Hello, today we will be seeing about overview and history of R programming. Today's session, these are the following objectives. What is R? What is S? History of S, history of R features, features of a free software, R drawbacks, design of the R system, and resources in R. What is R? This is a statistical programming language which is an open source package which is based on S language developed by Bell Laboratories in United States. It is actually a dialect of the S language. This is a very powerful language for writing programs that can be used in anywhere compared to C programming, C++, and a lot of analytical and statistical capabilities inbuilt. So as you can see, there are a lot of statistical functions inbuilt inside R programming. A lot of people contributed packages to expand this functionality, and there is cutting edge research going on currently in R programming. There is an open source community that supports R, and it's widely followed in rbloggers.com and Stack Overflow. This is a programming language, and hence generating the computer code to complete the tasks is mandatory. So what is S? As I said earlier, R programming is a dialect of the language S. S is a preliminary language that was developed by John Chambers and others at Bell Laboratories. S was initiated in 1976. This is an internal statistical analytical environment originally implemented as Fortran libraries. Fortran, as you can see, is a basic programming language which is called, the full form of Fortran is formal translation. The earlier versions of the language, they did not have any functions for statistical modeling. The statistical modeling functions were added to R in the recent years. As you can see, the S programming language was rewritten in 1998, rewritten in C, and it began to resemble that the R programming system that we have today. This is actually version 3 of the language, and as the John Chambers, the creator of S language, has a book called Statistical Models, and which explains the statistical analysis functionality of the R programming. This is often called as the White Book of R programming. Version 4 of the language was released in 1998, and this is the version we are currently using today. And there is one more book, Programming with Data by John Chambers. This is called as a Green Book, which documents the version of the language. Let's see the history of S programming language. In 1993, Bell Labs gave StatC, which is now currently called as Insightful Corporation, which owns an exclusive license to develop and sell the S programming language. In 2004, Insightful purchased the S language, which was earlier StatC, from Lucent for $2 million and is a current owner. Lucent is again an analytical company. In 2006, Alcatel purchased Lucent Technologies and is now called Alcatel Lucent. Alcatel is a mobile telecom provider in various parts of the world. Insightful sells its implementation of the S language under the product name S Plus and has built a number of fancy features. Most of them are graphical user interfaces on top of it. So hence the name S Plus. In 2008, Insightful is acquired by TIBCO for $25 million. Now TIBCO is the current owner of Insightful. The fundamentals of the language, it didn't change since it was formed in 1998. In 1998, S won the Association for Computing Machinery's Software System Award, which is a prestigious award for a software developer. Now we'll come to the history of R programming. This was created in 1991 in New Zealand by Ras Iaka and Robert Gentleman. Their experience developing R is documented in a 1996 JCGS paper. R was first announced to the public in 1993. Martin Mackler convinces Ras and Robert to use the GNU General Public License to make R a free software. Let's see the possibilities and the capabilities when a software is declared as free in the later part of the slide. In 1995, after R was made as free software, a public mailing list was created in 1996. R Help and R Devel, which is actually the development program for R. In 1997, the R core group is formed, containing some of the most associated people with S+. S+, as I discussed earlier, most of the GUIs were created on the base programming S, and S+ was formed. And these people were joined into the R core group as well. They control the source code for R. Even though it is a free software, there is a source code which will not be led to the people, and this will be used only by the core group. R version 1.0.0 was released in 2000, and the latest version 3.1.3 was released March 9th, 2015. The next version will be expected on April 2015. Now we will see about the features of R programming. What makes R so special that it became the buzzword of the analytics community? Syntax is very much similar to S programming, makes it easy for S+ users to switch over. Semantics are all superficially similar to S, but in reality are quite different. Runs on almost any standard computing platform or OS. It is available for all platforms and OS, as you can see in the download page of R programming, which I will tell later. Frequent releases, annual plus bug X releases, active development goes on for R features, R programming. As it is a free software, most of the people are welcome to develop R programming, enable capabilities for R programming as well. Let's continue with the features of R programming mode. It is quite lean as the software goes. The functionality is divided into modular packages, and these packages can be downloaded from various platforms into your system, and these packages can be used across. If you want to develop a functionality, you are most welcome to. You can develop a functionality for R and you can publish it in the open source community. Graphics capabilities are very sophisticated as it is open source funded and better than most stat packages available in the market. This is very much useful for interactive work, but it contains a very powerful programming language for developing new tools as well. There is a very vibrant and active user community that helps R programming to sustain this market and grow in this market. You can follow those groups in Stack Overflow and in rbloggers.com. Let's continue with the next slide. What are the features of a free software? As I said earlier, R programming is a free software. It has a general GNU license which is published only for free softwares, and this is supported by the open source community. What are the freedoms associated with levels of freedom associated with a free software? The freedom to run the program for any purpose. You may be an individual, a professional, or a company buying this software, and you have the freedom to run this program anywhere for any kind of purposes. The next level is a freedom 1. The freedom to study how the program works, what exactly happens in the backend of R programming, and you can adapt it to your needs. Access to the source code is a precondition for this. And there is the next level, freedom 2. This is the freedom to redistribute copies so you can help your neighbor. The next level is freedom 3. This is the freedom to improve the program and release your improvements to the public so that the whole community benefits. This is the purpose of a free software, to benefit other individuals and to support the open source community as well. Access to the source code is the precondition for this, as you would have guessed already. We will see the drawbacks of R programming. Essentially, it is based on a 40-year-old technology. There is little built-in support for the dynamics or 3D graphics. But there is an open source community which is supporting it really good, and they are developing a lot of R tools which will help you in creating 3D graphics as well, which will be overcome in the future. So this may be a drawback in the current situation alone. And the functionality is based on consumer demand. Whatever functionalities you require from the R package might not necessarily be available in the current version. If you want to create a functionality, maybe you can create it, or you can hire someone who is well versed in R programming and you can ask them to contribute. Objects must be stored generally in the physical memory, but there have been advancements in this field too. I'll tell you about that later once we get into the parameters. R programming is not ideal for all possible situations, but this goes with any software, free or paid, whichever the case may be. Now we'll move on to the design of the R system. The R system is divided into two conceptual parts. The base R system that you can download from CRAN, which will be available when you search it on Google itself. You can get the link for downloading R, and there is other packages which are modular, which you can create, which you can extract from other users as well. So the functionality is divided into number of packages. The base R system contains, among other things, the base package, which is required to run R, and it contains the most fundamental functions. There are other packages in the base system as well, which includes utils, stats, datasets, graphics, GR devices, grid, methods, tools, parallel, compiler, splines, entire course. There are also recommend packages like boot, class, cluster, code tools, foreign, kernsmooth, lattice, MGCV, NLME, RPart, survival, mass, spatial, NNet matrix. Looking more into the design of the R system, there are many other packages available which you can download from the CRAN webpage. There are almost about 4,000 packages on CRAN, and they have been developed by users and programmers all around the world. And there are also many packages associated with bioconductor project. You can see the URL given there, http://bioconductor.org. You can download those packages from this URL. And as you can notice, R programming is an open software, and there are multiple packages available for it in people's personal websites also. There is no reliable way to keep track of how many packages are available in this fashion. Now the resources for R, and I will give you the list of useful books also. The URL that you are seeing on the top is where you can download R package, which is depending upon your processor capability. If it is a 64-bit OS, you can download the 64-bit version. Both 64-bit and 32-bit comes along, and once it is installed, you can use the 64-bit or 32-bit based on your OS. There are a lot of books available and resources. An introduction to R is available in the same CRAN website. Writing R extensions, R data import or export are also available in CRAN website. R installation and administration, mostly for building R from the sources, and R internals. This you will get into once you are entering into the advanced level of R programming. Now to see the useful books for R programming: Standard Text Chambers 2008, written by John Chambers. Software for Data Analysis, Springer. Chambers 1998, Programming with Data, Springer. Venables and Ripley 2002, Modern Applied Statistics with S, Springer. Venables and Ripley 2000, S Programming, Springer. Pinheiro and Bates 2000, Mixed Effects Models in S and S+, Springer. Morel 2005, R Graphics, Chapman and Hall, CRC Press. Other resources: Springer has a series of books called Use R. A longer list of books, you can check it out at www.rproject.org/doc/bib/rbooks.html. Welcome to the second session of R programming. Today, we will discuss about the data types and basic operations in R programming. Today's objectives for the session are: we will be seeing a lot about the data types available in R, as well as how to input and output values, and a lot other functionalities in R programming. The first thing we'll be seeing in R is objects. Next will be numbers, attributes, entering input and printing outputs, vectors, lists, factors, missing values, data frames, and names. We will see in detail about all these in this session. R basically has 5 atomic classes of objects. R programming is very much different from C programming and C++, but there are some similarities as well. The 5 atomic classes of objects in R programming are characters, numeric, which are real numbers, integers, complex numbers, and logical, which will contain true or false. We can call it as Boolean also. The most basic object, which is by default in R programming, is a vector. A vector can only contain objects of the same class, which means when you define a vector in R programming, either it will be a vector of characters, or a vector of numeric real numbers, or a vector of integers, or it can be a vector of anything, but all the objects within a vector will belong to the same class. There is one exception to this, which is called as a list. This is also represented as a vector, but it can contain different objects of classes within it. We will see a side-by-side example to this in the following slides. And there is a possibility that we can create empty vectors using the vector function. Now we will see about numbers. Numbers in R are generally treated as numeric objects, that is double precision real numbers, which is similar to the double object in C++ or C. If you want to explicitly specify that it is an integer, you have to specify with the L suffix. Example: entering 1 gives you a numeric object, but if you enter it as an 1L, it will explicitly give you an integer. One of the best things about R programming is that there is a special number here, which is denoted by INF, which is short form, and it represents infinity. For example, when you divide 1 by 0, the output is infinity in mathematical terms. INF can be used in ordinary calculations. Example: 1 by infinity is 0. These kind of calculations it is possible to do in R programming. And there is also a special number, you can say it as a number, but it actually denotes not a number. It is represented by NaN, and which denotes an undefined value, a number which is not defined. For example, 0 by 0. It is neither infinity nor denotes to a number, which is an undefined value, and it's denoted by NaN, which can also be thought as a missing value. Next we will see about attributes. As you can see, R objects, not just R objects, in general objects will have attributes. For example, names, dim names. Dim names are nothing but dimension names. And in case of matrices or arrays, dimensions, class, length, and you can define other user defined attributes as well, which you can call as metadata, which is nothing but information about data. Attributes of an object can be used using the attributes function. Now we'll enter into the coding part. The first thing we'll be seeing is entering basic input into the R programming console. So Here I've given a small example so that you can view this later on. The arrow symbol followed by the hyphen denotes the assignment operator, which is nothing but if x equal to 1. You are assigning the value 1 to x. The next is the print function which is available in R programming. If you print of x, it will give you 1. I'll show you a short example now. Now the value of 1 is assigned to x. And as you can see, this is the console for R programming. Where this is a 64-bit console as it is a 64-bit OS. In this console, you have a lot of functionalities available to open, edit, view, and a lot of other functions as well, which you can explore. Now I have assigned the value 1 to x. This is the console where you type in all your inputs or whatever the code you need to give in. Now this is the value 1 is assigned to x. Now to print x, either I can go use the function of print and print explicitly the value of x. As you can see here, this denotes the first object inside the vector x and the number 1. Now we'll continue with the slide. There are other things possible as well. Message hello. Now here, as you can see, hello is assigned to message. So when you want to print x, print message, you can just print it. As I've entered with a capital P, it shows could not find function. It's actually with small. Now as you can see, the message hello has been displayed. Now our language also has a grammar associated with it, which follows certain semantics and syntax. Here for example, when you assign double hash to x, it will give you an incomplete expression. The hash character indicates a comment. Anything to the right of the hash, including the hash itself, will be ignored, which is a comment. As in the programming world, a comment is used to describe what exactly the line of code does. Here, the assignment operator after x is followed by hash, which means nothing is assigned to x and it will give you a incomplete expression. Now we will move on to the next thing, evaluation. Now I showed you about explicit printing where I use the function print of x to print the value of x. When a complete expression is entered at the prompt, it is evaluated and the result of the evaluated expression is returned. Either it can be auto printing or explicit printing. Now I'll explain you from the sheet. We'll go ahead with the same example. When you assign values 1 to x, it is assigned to it. Either you can use printing, which is called as auto printing. When you just print x, it will print it, the value of x. Or you can explicitly type print of x to print the value of x. There are two ways of printing it. There is one more thing I wanted to tell you here. A shortcut key is available in R to clear the screen in the console. Control plus L will clear the console. Now moving on to the next thing. As I said earlier, the 1 indicates that x is a vector and 5 is the first element. Here I assigned value 1 in the example and 1 was the first element, and that's why 1 was displayed in square brackets. Now the next steps of printing. There is a thing in R where you can create sequence of numbers in a single vector. For example, let's say I want to create a vector where I can assign the numbers 1 to 30 in a single vector. How I can do that? I can assign 1 to 30, 1 colon 30, which will give 1 to 30 and it will assign it to x. Now if you print x, you can see that there are 1, 2, 3, 4 till 30 assigned to x. X is a vector of integers here. The colon operator is used to create that integer sequences. Going on to the next part, how to create vectors. The function c followed by set brackets can be used to create vectors of objects. As I told you earlier, a vector is nothing but a collection of same class of objects. It can be any numbers, any number of values inside the vector, but everything has to be in the same class. Here I have shown you some basic examples to create a numeric vector, a logical vector again, a character vector, an integer vector, and a complex vector. We can do all together in the R console now. Control L will clear the console. Now I want to create a vector which is numeric. Now I'm trying to create a vector which contains two values, 1.5 and 1.6. Now the vector is created. To display the vectors, again I have to display it using X and it displays 1.5, 1.6 are assigned to the vector. Same way you can create a logical vector. Everything has to be in caps. Now if you print, the value of x, you'll get true and false assigned to it. Now we can create character vectors a comma b comma c. Now I want this vector to contain the values a, b and c. Now the object a was not found is the error returned. What exactly it specifies is this is not a predefined object in R. This is a string or a character which should be represented only by double quotes. Now this vector is created. This is a character vector, and when you display this character vector you will get a, b and c inside. Now again in the same way you can create an integer vector and a complex vector. As we have already seen the integer vector, I'll show you the complex vector. Now I have added two complex numbers. One is 1 plus 0i and the other is 2 plus 5i. These are called complex numbers as there are imaginary parts associated with the real numbers. Now when I display this x, I'll get 1 plus 0i and 2 plus 5i inside the vector. Now we'll move on to the next thing. So using the vector function, we can create a vector. Earlier I showed you the function c followed by the set brackets. Now the function vector followed by the set brackets. Now what are the parameters passed in this vector function? The first thing is what type of vector you are trying to create. Either it is numeric or logical or character or complex or integer. And the length which what you are defining the vector. For example, I'm using Ctrl L to clear the screen. Now when I add a vector using the vector function, I want to create a numeric vector with length equal to 10. Now this vector is created. As this vector is not assigned any values, it will display only zeros. From 1 to 10, all 10 values in the vector are zeros. Now we'll move on to the next part of mixing objects. So here I'm trying to create a character vector, but instead I have a numeric value also in the same vector. So what does happen in this? In the first example, I have shown you y is assigned a vector with values 1.7 and a character a. So there are two sets of objects being added to the same vector. You can see that in the next case also a logical value is added along with a numeric character, and the next thing you can see a character being added with a logical value. So what happens here is that in the first case the vector itself will get converted into a character vector. In the next case it will be a numeric vector, and the next case it will be a character vector again. So what exactly happens here is a term used in R programming called coercion, which happens so that even if you add a vector with multiple classes of objects, it will convert to the same class of objects. Now we will see more about coercion. There is a thing called explicit coercion in R programming. As I showed you some examples earlier, in the previous case, when we try to add a numeric and a character into a same vector, you will see that it converts into a character vector. Now in this next case, I'll show you about explicit coercion. Here you can define what the object can be. So an object can be explicitly coerced from one class to another using the as.star function. The star actually defines like what you want to add in that. For example, Ctrl L will clear the screen. I am adding a integer value to x. Now class of x will tell me what value is there. It's a numeric value. Pardon. I've added a numeric value to class x, and the class of x is giving me that 1.6 is numeric. Now what I can do is that I can convert this numeric into a logical or an integer. So if I try to do a as dot numeric logical of x, it will turn that 1.6 into true, which is actually any number greater than 0 will be declared as true. If it is 0, it will be changed as false. Now this is called explicit coercion, as a numeric is converted into logical by using this as dot logical of x function. Now the same way you can create as dot numeric, as dot logical, as dot character, as dot complex. You can coerce any class of object into a different class using this explicit coercion function. Now we will see about a thing called nonsensical coercion, which means there is no logic in what we are coercing. For example, if you are converting a character vector into a numeric vector using as dot numeric of x, it will return na, which means the coercion cannot happen as a character cannot be converted into numeric. Again, the same way, if you try to do the same thing for as dot logical of x, you will get na again, as this kind of coercion cannot happen. Now we'll see about matrices. So matrices are vectors with a dimension attribute. The dimension attribute is nothing but it itself is an integer, as you can see where I'm pointing the mouse, 1, 2 and 3, which indicates column 1, column 2 and column 3. This is called as a dimension attribute, which defines the first column, and this is denotes the first row. And na is located at 1 cross 1, which means it located in the first place, first row, first column. So this is the dimension attribute which every integer vector will have. So for example, here I want to create a matrix. The function for creating a matrix is matrix of the number of rows and the number of columns. I'll show you a clear example. Clear the screen. Now I want to create a matrix M, which will contain the number of rows equal to 3, comma, number of columns equal to 3. Now the matrix is created. As the matrix is not filled with any of the values, the matrix will display only na in all the places. Now you want to see the dimension of matrix using dim. It will tell you the number of rows and number of columns for the matrix M. Here it is 3 rows and 3 columns. This is the dimension attribute is specifically for a matrix. Now which you can use the function attributes of M to display the same dimensions and other attributes as well, but here we don't have any other attributes, we have only the dimension. So it displays 2, 3 here, and in this example it will display 3 and 3, which means there are like 3 rows and 3 columns in the matrix. Now we'll continue with the matrix. So we created a matrix with no values inserted, just declare the number of rows and number of columns. So what if I want to add a set of integers into that? So it is constructed column wise, which means when I try to add a integer sequence in this matrix, it will start from the upper left, it will fill values till it ends. So let's say I want to create add 6 integers into a 2 cross 3 matrix. It will add 1 in 1 1 and 2 in 2 1 and it's so on. 3 in 1 2, 4 in 2 2. I'll show you the clear example here. Now I'm creating the same matrix where I wanted to insert values 1 to 9 in a 3 cross 3 matrix. One should be familiar with the concept of matrix to understand what exactly happens here. This is a 3 cross 3 matrix, so which will contain 9 values, and the 9 values will be integers added to it. Now when I display M, you will find that 1 2 3 column wise added, 4 5 6 and 7 8 10 all column wise added. Now we'll continue with more. We created vectors earlier using integer sequences. Now is there a way to convert this integer sequences into a matrix? There is a possibility that for a vector there is a dimension associated with it. So when you change the dimension, it will automatically change into a matrix. For example, there is a matrix created, there is a vector created which contains the values 1 to 9. Now I want to convert this vector into a matrix. So how I can do that is change the dimension of this matrix to contain, just change the dimension of this matrix. So now this vector has become a matrix. Next we'll go with C binding and R binding. So these are concepts associated with only the matrices. Either I'll explain you in detail about this. Matrices can be created by column binding or row binding with C bind and R bind functions. So these are functions. C bind is nothing but column binding and R bind is nothing but row binding. Let's say there are two integer vectors which contain the values 1 to 3 and y which contains 5 to 10. Now when you display X, it will show you 1, 2, 3, and when you display Y, it will show you 5, 6, 7, 8, 9, and 10. Now I want to create a matrix which will contain the values of X and Y in a column. How can I do that? So if I use a column bind of X comma Y, it will give me this. Now as you can see here, X is a vector with only 3 values and Y is a vector with 6 values. So when I create a column bind, it basically takes X and Y as 2 columns and add it together in the matrix. Now X becomes 1 column and Y becomes 1 column. As Y had 6 numbers, it displays the values 5 to 10. But X, in the other hand, it had only 3 values. So what happened is that the same values are replicated in the next cells also. So X has 1, 2, 3 and the next is 1, 2, 3 again. Now this is called C bind. Now if I want to do a R bind of the same X comma Y, I'll get this, which will have same but in a columnar in a row fashion. 1, 2, 3, 1, 2, 3 in X and 5, 6, 7, 8, 9, 10 in Y. Now we'll move on to lists. As I explained to you earlier, lists are a special type of vectors where you can have elements with different classes. Lists, the declaration of list, as you can see, is similar to that of a vector. I've cleared the console. Now if I want to add a character, an integer, a numeric, a logical value into the same thing, it will say this is an unexpected error. And why does it happen? Because X is getting assigned values of multiple classes of objects. Now if I want to create a list, if I create it as a list, this will accept as a list is nothing but a collection of vectors of different classes. Now as you can see, there are 2 dimensions indicating that 1 1 contains A, 2 1 contains 1, 3 1 contains 1.2, 4 1 contains 2. This in itself, the A is in itself is a vector. This again is a vector, this again is a vector. Whereas the list is a collection of vectors in it. Next we'll move on to factors. Now factors are used to represent categorical data. If you have worked in market research, if you want to identify demographics, factors can be used. If you want to classify the human beings, they are mostly classified into males and females by gender, and this is what you call as a categorical data. It can be either unordered or ordered, and it can be thought of as an integer vector where each integer has a label. And there are special modeling functions like LM and GLM in R for treating these factors. So what makes like factors different is that they have labels which are self-describing for the factors itself. Let's say if you want to describe males by 1 and females by 2, there might be some sort of confusion in the data which can be expected in the future. But when you declare the variable as male or female, it is more self-describing than anything else. So whenever creating a factors, so if you want to create a age group factor, it should have values like 15 to 20 years, 21 to 25 years, 35 to 30 years, 35 to 45 years, like that. So it will be self-describing in its nature. Now, moving on to the next part, how to create a factor. Now, here I want to define a factor which will have values only yes or no. These are categorical. The question may be anything, but the answer is either yes or no. Now there are 5 values in the vector which are character vectors and when you create this factor, let's say X contains the values yes, no, yes, yes. Now X is a factor which contains the values yes, no and yes, yes. There are only 2 levels possible in this. One is yes and one is no. If I wanted to create a factor which contains whether they are male or female, then the levels will be male, female. Now using a table I can represent X which will show you how many values are there, which corresponds to yes and which corresponds to no. Now as you can see, there is one value for no and three value for yes. So that's why it shows like that. Now this table can be used in multiple purposes in analytical terms. So when you use unclass of x, what happens? Now as you can see, a factor's values are categorized into integers. For example, yes is categorized as 2 and no is categorized as 1. So the attribute levels will be no, comma, no and yes, and no is indicated by 1 and yes is indicated by 2. We have unclassed the factor by removing the variables yes and no and converted them to integers, which will also have its uses when you are going for data manipulations. Moving on to the next part, we can set the order of the levels. For example, in the previous example that we saw, no was declared as 1 and yes was declared as 2. Now, if you want to set the order of the levels, you can set using the levels argument. This might be important in linear modeling because the first level is used as the baseline level. For example, while creating the x factor, you can define the levels by putting the values s, no. Now the levels are defined as yes, no. As you can see earlier, the levels were no, yes, and now it is yes, no. Moving on to the next one. Now we'll see about missing values. In data collection, in any company that is working with data, there is a task to handle these missing values. So what are these missing values? Missing values, as the term indicates, the values are missing from the data itself. And to handle what you are going to do with these missing values is an important business decision, as this will affect your insights derived from the data. Now, here in R programming, missing values are denoted by NA or NaN, which means not a number, for undefined mathematical operations. Now, there is a function called is.na which can be used to test objects if they are na, which means the values are missing, and the same thing for is.nan. So na values, they also have a class. So there can be either integer na, character na, etc. A nan value is also na, but the converse is not true, which means a nan value can be na, but na might not be possibly nan. Now we'll go with the next thing. There is a vector defined here which has the values 1, 2, na, 10, 3. So now let's check with this example. X contains a vector 1, 2, 3, na, 4, 5, 6. Now the vector is created. Now if I want to check whether this vector contains na values, I can use this is.na function, which will display the logical values for the x vector. Now it is false, 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 true, which indicates that there is a missing value inside this. Now the same way you can use is.nan. Here in this example, you can clearly see that it shows false, false, true, true, and false for nan as well as na. But here, if you see, here it is showing false, 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 and false, which indicates that nan will not be able to identify na, but na will be able to identify nan. So that's the difference between not a number and na. Now we will move on to data frames. Data frames are used to store tabular data. So when you have a table of values which contains multiple columns and you want to add it into the data set of R, the object that you have to use is data frames. These are represented as a special type of list where every element of the list has to have the same length. As we saw earlier, a list is a set of vectors which will have different class of objects, but here a data frame is a special type of list. Every element of the list has to have the same length. Now a list will correspond to a particular column in a table. Imagine a table side by side with this data frame, and the data frame will have a particular list of elements, and each element will correspond to the columns in the table. Unlike matrices, data frames can store different classes of objects in each column. Matrices must have every element to be in the same class. Data frames also have a special attribute called row.names, and they are usually created by calling read.table or read.csv. You can either read it from a table or use a CSV file, or which is actually an Excel file stored in CSV format, and you can read it from there. Or you can convert it to a matrix by calling data matrix. Now there are two elements in X, the data frame X. I'll show you an example. Here the first element is called FOO and the next element is called bar. The first element is a list with integers 1 to 4 and the next element is a vector with logical values. Now the number of rows is 4, the number of columns is 2. The number of columns shows is the number of elements in that list. Now we will move on to the names. Any object in R can have names. This is useful when you want to write a code and which will have self-describing objects. When someone else views this code, they will also be able to get a good sense of what's happening in the code. Now let's say I create a vector. I create an integer sequence with 1 to 3 values. Now using this names of X function will give me if there are any names predefined for 1, 2 and 3. Now as there are no names defined, it will leave me with null. Now if I want to add names to that, you can add it by using names of X. This names of X will be a vector which will be assigned to the values 1, 2 and 3. Now let's say I want to divide by A, B and C. Now the names have been assigned. Now if I see names of X, you will get A, B and C, and the values of X are 1, 2 and 3. For 1, 2 and 3 you have assigned names A, B and C. Now again, as I said earlier, any object can have names. So do lists. So let's say there is a list which contains values A, B and C, values 1, 2 and 3. Each are assigned a name A, B and C. Now it is named. The value 1 is corresponding to A. This kind of naming will help you retrieve the data also from the list created. Again, names in terms of lists and objects, you can also use it for matrices. Let's say there is a 1 cross 4 matrix and the number of rows is 2 and columns is 2. You can add using dim names of M. We'll do that in the console. Let's create a matrix which contains values 1 to 4 and number of rows is 2, comma, number of columns is 2. When you display the matrix, you will see 1, 2, 3, 4 added to it. And if you want to add the names A, B, C, D to each of the rows and columns, what you can do is dim names of M. M denotes the matrix here, and you want to add a list of vectors which will be the names of the matrix. Now I'm trying to assign. As you can see, the dimensions have changed from 1 to 1 to 2, A, B and C, D. A denotes the first row, B denotes the second row, C denotes the first column, D denotes the second column. Now this is how you create names for matrices. These are very useful when you want to access certain values of the matrices using just names. To summarize what we learned from this, there are data types. The atomic classes are numeric, logical, character, integer and complex. We learned about vectors and we learned about list, which are a special type of vectors where you can have multiple classes of objects, and we learned about factors. We learned about how to handle missing values. We learned about data frames wherein you can have tabular formatted data into the data of R, and we learned about naming the objects. We'll conclude the session with this. Now welcome to the next session in data types in basic operations. This session will have the following objectives. We will see about subsetting in list as well as matrices. We will see about partial matching, vectorized operations and removing NA values in detail. We saw that about removing NA values in the previous session, but we will see in more detail in this session. Subsetting. What exactly is subsetting? You have a set of data which contains a list of values, for example 1, 2, 3, 4, 5. Now you want to extract only values which are greater than 3. So from 1, 2, 3, 4, 5 you are extracting only 4, 5. So extracting this 4 and 5 from the set of 1, 2, 3, 4, 5 is called subsetting. You actually created a subset which contains values 4, 5 from a set of 5 individual elements. So here R provides a list of operators that can be used for extracting subsets. For example, the single square bracket, which it can be used to extract a same class of object from the previous one. It can be used to select more than one element, and the next set is double square brackets, which can be used to extract elements of a list or a data frame, which will normally contain it is similar to an array within an array in C programming. It can be used to extract a single element and the class of the return object not necessarily be the list or a data frame. Now we can use dollar to extract elements of a list or a data frame by name. Semantics are similar to that of double square brackets. Now we'll see subsetting examples. Now let's say there is a set of values. We'll replicate this in the console. Let's say we have a set of values inside a vector R, vector X. It contains 6 values A, B, C, D, D and A. Now when you print this, you'll get all this A, B, C, D, D, A. Now I want to extract only values B, C, D, D, which means which are greater than A. That's right. You can also use operations on characters as well. Now I want to create a subset where we have values greater than, I've used a single set of brackets which will display only B, C, D, D, which will exclude A and A. Now I want to create a logical vector which will contain only the operators, only the values of resulting operation. X greater than A is nothing but a operator which will return either true or false. If A is greater than A, it will return true, but it is not, so it will return false. And same way for B, same way for C, same way for D and others. Now this U will contain only Boolean values, false which indicates A is not greater than A, and true indicates all these values are greater than D. Now you can use these, the value U inside X, to extract specifically BCDD, which corresponds to true. Now I say if I extract X of U, it will give me only BCDD, which will remove these A values. Now let's move on to the next one, subsetting a matrix. The same way we are subsetting a list, the same way we are subsetting a vector, we can subset a matrix as well. For example, let's say there is a 1 cross 6 matrix. Let's say there is a matrix which contains the elements 1 to 6 and the number of rows is 2 and the number of columns is 3. Now we have a matrix like this. Now we want to extract single elements from this. Let's say if you want to extract the value 5, the dimensions corresponding to 5 is 1, 3. Now if you use this 1, 3, we'll be able to extract the value 5. This is what subsetting actually is. Now if I want to extract the entire row 2, I can do X of 2, which means the row 2 and the column name is not specified, which will indicate R to extract only the second row. Now 2, 4, 6 alone is extracted. Moving on to the next part, subsetting a matrix. When a single element of a matrix is retrieved, it is returned as a vector of length 1 rather than a 1 cross 1 matrix. When a matrix, you are creating a subset, the subset is not a matrix. That's what I'm trying to imply here. This can be turned off by using a setting called drop, and if this drop setting is mapped as false, the value returned will be a matrix as well. For example, in the same example that we saw earlier, we extracted X of 1, 3, which is 5. Now let's say I want to extract the same. This X of 1, 3 is returning the value 5, and this is a vector of length 1 rather than a matrix itself. So let's say I want to extract x of 1 comma 3, but now I want this as a matrix. Now if I set this as false, the resulting, pardon me for the mistake, I used a set bracket. So if I use false, the resulting set subset will also be a matrix. Now moving on, a single column or a single row will also give me a vector when you are subsetting it, and it is not a matrix. Same thing, we'll go with the same example of extracting x of 2 comma and extracting the second row. Let's say I want to extract the second row, but this time I want it as a matrix. Now this will give me a matrix 1 cross 3 matrix which contains the values 2, 4 and 6. Now moving on to subsetting of lists. Let's say we have a list which contains two elements. List of, let's say, A equal to 1 to 4. It's a sequence of 1 to 4, comma B is a numerical value. I've created a list. Now in this list, if I want to extract only the first element, x of 1, it will give me $A, which will give you the sequence of 1, 2, 3, 4. The first element is nothing but an integer sequence, and the next element is a numeric value. As you can see here, using the double brackets, you can exactly do the same thing again and again. So let's say I want to extract the first element. Within the list of x, I can extract 1, 2, 3, 4. And the same way you can use x $A, which will give you the first element. Same way you can use x $B, which will give you the second element. The same way you can use the double brackets also to extract either using the name A or the first element. It also give you the same value. So there are multiple ways to extract subsets from a set. Now how can we extract multiple elements of a list? Let's say I want to extract 2 of 3 elements in a list. For example, let's say there is a list which has elements A, which is a integer sequence, element B, which is a numeric value, comma C, which is a character sequence. Now this is the list. Now I want to extract only A and C from this list. How can I do that? If I use 1 comma 3 in the single bracket, I can extract this. The incorrect number of dimensions, as I have entered as a number of dimensions in X. Now to extract elements 1 and 3, I have to create a vector which contains 1 comma 3 and then extract those values alone, which will give me elements A and C. Now moving on to the next part, the single operator can be used with computed integers. These are like double square bracket operator. Dollar can only be used with literal names. For example, in this string, either it is $A or $C. This is the way we can use the dollar symbol, which can be used with names of the elements. But here you can use with computed indices also. For example, let's say we create a name equal to A. Now I want to use this name to extract only the element A from the list X. I can do that. Now I use name to extract the first element 1, 2, 3, 4 from the vector X. The same way we can use $A like I said earlier, but if I use $name, this will return null as this is a predefined character vector. It's a predefined character vector. Now moving on, let's see the subsetting nested elements of a list. Let's say the double square bracket always can take an integer sequence also. Let's say we create a list which has A 1, 2, 3 Now we are seeing about subsetting nested elements of a list. Let's say there is a list within a list 1, 2, 3, and then there is a vector which contains values 1.5, 1.6. Now this is the list created. Now if I want to extract only this value 3, how can I extract it? Is if I use x of double square brackets, and if I use 1, 3 without the quotes, and if I use this, I'll be directly pinpointing to this 3. Now I should be declaring the C of 1, 3 as it is a vector. Yeah, now it is pointing to 3. Now we are able to extract this. Now let's move on to partial matching. Let's say we have a list which corresponds to ABC, AARD something equal to 1 to 5. Now if you display this x $A, you will find 1, 2, 3, 4, 5. Now let's say the dollar symbol is actually retrieving 1, 2, 3, 4, 5 because there's a partial match with the element AAARD. That's why you are able to extract 1, 2, 3, 4, 5. The partial matching is allowed in dollar, whereas in this case x double bracket quotes A, if I use this, it will return null. This A is not matching with this. Now if I use the exact parameter as false, I'll get 1, 2, 3, 4, 5. Partial matching works in case if you are using exact. Now removing NA values. Last time we saw about identifying NA values using s.na function. Now to remove NA values, how can I do that? Let's say there is a vector which contains values C of 1, 2, 3, NA, 4. Now I want to, when you display X, you will find that there is an NA value inside this. So how can I remove this NA value from the list, from the vector? Let's say I define a value bad which will have, now I'm using this is.na function to identify the NA values in X and assign it to bad. Now if you see what the values in bad, it will be a boolean thing containing false, 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 true and false. The true indicates there is a NA value within X. Now how can I remove it? If I use X of not symbol, which is an exclamatory mark, and use bad, it will remove NA value and it will give me 1, 2, 3, 4. This is normally used in data cleaning purposes, where you want to remove NA values from your data and the data will be more cleaner than before. Now moving on, removing NA values. So let's say you want to take the subset without the missing values. How can we do that? Let's say there is a vector X which contains 2, 3, NA, 5 and this. And there is a vector Y which contains B, NA, C. It's a character vector which has an NA value. Now you can see this. Now if you want to have only the good values, which I'm indicating here, which are not NA, so using complete dot cases of X, Y, which will give me, okay, as the argument lengths are not same, now I have to change the argument length of Y to contain one more, as it was earlier having 4, now I'm having 5. Now if I use good of complete case again, it will work because the argument length for Y and X are now same. So if I use good, now you get true, true, false, false, true. Now if I use X of good, I'll get only 1 to 5, which means in 1, 2, 3, NA5 corresponding to 3 there was an NA in Y. That's why I was not able to get. It combines both X and Y in a columnar fashion and finds only the good values of X and now the good values of Y, A, B and D. So now we have removed all NA values corresponding to each and everything. Now moving to vectorized operations. So like many operations in R are vectorized, making code more efficient, concise and easier to read. Let's say you have X to be a integer sequence 1 to 4 and have Y to be a sequence 6 to 9. Let's say you want to add both. It adds 1 plus 6, 2 plus 7, 3 plus 8 and 4 plus 9. So these kind of operations will make it even more simpler. As you can see in these examples, if you use x greater than true, it will give you a boolean value false, false, true, true. For whatever values which are greater than 2, you will get true, and which are less than 2, less than or equal to 2, you will get false. Same way for greater than 2 and double equal to 8, which means the value equal to 8, which is true for only 8, and others it will be false. Now you can do x into y also, which will give you 6, 14, 24 and 36. It will come to x of 1 to y of 1, it will multiply the same way for x divided by y. Now moving on to vectorized matrix operations. The same way we did for vector operations, same way it corresponds to matrix as well. We have a matrix 1 to 4 matrix, and we have a same level of matrix here also. And when you multiply that, it should have the same number of elements to perform element wise multiplication. So to perform true matrix multiplication, you can find this is element wise. So 1 to 4 and 10 comma 4, it get repeated, which means 10 4 10 4. So it will be 1 into 10, 3 into 10, again like 2 into 10, this is 4 into 10, which here this 10 is repeated 4 times. The matrix contains value 10 4 times. So same way for x divided by y, and to perform true matrix multiplication, you have to perform it with x percentage star percentage y. This I will not do in the console, as you should try this at home and you can learn better from it. Now we conclude with this session. We will see in the next session. Hello people. Today we will be seeing about reading and writing data in R. Previously we saw about creating objects and all the manipulations that are possible in R programming. Now we'll get into the class of reading and writing data. So what is the process of reading data? Let's take an example of, if you have an earlier experience with C programming or C++, you would have noted in the commands C in, C out. C out is used for printing and C in is taking characters. And in same way in C programming also, using print, scan, those kind of things, variables that are used to just read the variables. Here, reading data points to not just reading data from getting input from the user, also it points to taking data from files which contain the data. Let's say about there are a few principal functions regarding reading data into R. Read table, read.table, which will help you reading table data into the R dataset. Read.csv. CSV is an extension which is a format similar to Excel. These can be used, to read tabular data. Next is your read lines, which will be used for extracting lines from a text file, which may be any character set or a number set, or it can be anything else. And source. This is for reading in R code files. And dgate for reading in R code files. This is inverse of dput. I'll tell you later what is that. And load for reading in saved workspaces. And unserialized for reading single R objects in binary form. Let's say you have a object in R. This unserialized will help you to read those objects in binary form. Writing data. There are same analogous functions with respect to reading data for writing data as well in R programming. Write the table, writing inside a CSV file or a table created. Write lines, writing lines in a text file. Dump, dput, save, and serialize is opposite to unserialized that we saw in reading data. Moving on, how to use read.table to extract data from a tabular structure. It is one of the most commonly used functions. As you have already known, R programming is used for gaining statistical conclusions from tabular data, which is one of the main uses of R programming. Now, which is why reading data from table is one of the most commonly used functions. So here, read.table has a lot of arguments. As you would have aware, in programming language, an argument is something which you can pass into a function, and using that, the function will extract the separate the things that are needed. For example, here the file read.table has a parameter called argument called file, which is the name of the file or the connection from which the data needs to be extracted, and header, which indicates if the file has a header line, which is similar to all your HTML and XML pages. Sep, which is a string indicating how the columns are separated. And call classes, it's a character vector which indicates the class of each column in the dataset. Which column does it belong to? Which class does it belong to? Each of the column, it may be a numeric class, or it can be a character class. This call classes is a character vector which indicates which column which class the column belongs to, and n rows, which is the number of rows in the dataset. Comment.char, which is a character string. Again, this indicates whether it is a common character. Like I said, hash key can be used to write comments in any table. So if say there are like 7 rows in a table and you have a comment which tells you what are the functions of each of those columns in the table, these comments will be marked by hash, and this comment that character char will tell you which is the common character. And skip, when you are reading data into the R data set, you can use the skip argument to skip the number of lines from the beginning to insert into the data. Strings as factors. This is why there is a small discussion that happens whenever you have character variables in your table, and whether they should be coded as factors. It depends on what our necessity is. Character variables can be kept as character variables and extracted into our data set, or you can go and code them as factors. As I said earlier, factors are used for descriptive character sets. For example, male, female, those kind of character sets are used as factors. Now we'll see about read.table in specific. Read.table for small to moderately sized data sets, you can just specify read.table without any arguments. The arguments that we discussed earlier, we don't have to use if the data is very less. So let's move on to the R console, where we can see a sample reading of data from a sample. Now here I have the R console. Earlier I didn't tell you about setting up a working directory for R. So whenever you save your files which needs to be read in R, you need to specify your working directory here, change directory, and the specified directory, the location of where you have kept the file. So I have kept it as here R directory, and I set it as the working directory. Now I have a sample file which have the variables A, B, C, D, E corresponding to their, and numbers 1, 2, 3, 4, 5 corresponding to each other, which means the data exists in 2 columns, 5 characters and 5 numbers, each corresponds to each other. So using this, what we have to do is like read this data into our data set in R. So let's say as the working directory is set, you don't need to specify where the location of the file is. Let's say I want to create a variable X which will take the tabular data. Sample.txt is the file name that I created earlier. Now I have read this. There is a warning message as the table header is not available, the argument in this. And now if you display X, you will get the 2 columns A, B, C, D, E, 1, 2, 3, 4, 5. Now this would have showed you the possibility of what data can be read into R. Every columnar tabular data can be taken into consideration, and the manipulations can be done on those data. Now seeing more about R, what it does automatically, it skips lines that begin with a hash. Hash, as I told you earlier, will indicate whether it's a comment or not. So R will automatically skip this, and and you should be able to figure out the size of this. R automatically does it, how many rows are there and how much memory needs to be allocated. So based on the number of rows into the number of columns in the data, R will automatically assign the space required to keep the data in it, and it has the ability to figure out what type of variable is in each of the columns. In R, the data in the first set is character and the second is an integer, and R has the automatic ability to find out what type of variable is in each of the column. And if you want to specify it explicitly to R, which character set you are taking from, which class of variables you are taking from, that will make it run faster and much more efficient than it happens. Moving on, how to use read.table to extract data which are larger in size. So with much larger data sets, we have to do some specific things which will prevent R from stuck on the data. So you should specify certain things which will make R programming run much faster. First of all, read the help page for R read.table, which contains many hints for your possible data extraction, and depends upon the necessity of you. And there is much more newer possibilities coming into extracting data when it comes to statistical analysis. So you can always make a rough calculation of the memory required for your data set. Let's say you have a 4 GB RAM, and if the data set which you are going to pull from your table, if it is larger than the amount of RAM, you can just you don't have to do it that way. Maybe you can split the data and do it part by part, but you don't have to do it directly. And you can set comment dot character equal to null if there are no commented lines in your file. R automatically searches for this comment dot character, which is your comments in the data, and you can stop this by setting comment dot character. If there is no comments in your data, you can just set this comment dot character equal to null, and this will prevent R from searching at this comments in the data. Moving on, so you should use this call classes argument, which when you specify this option, instead of going for the default, it will make read.table run much faster, and it was often indicated as twice as faster than what it runs when it is in default. So in order to know this, like what you have to do, you should understand your data first, and what classes of data, what classes of columns are existing in your data to do this. Let's say you have a column, numeric column, then you can just set call classes equal to numeric, and easier way to figure out the classes of each column is the following way. Let's say you have a table data table.txt. As I have a sample table, I can show you that. And let's say you want to find the classes of all the table sample.txt. I'll show you it in R. Moving on to R console, setting a variable called initial, which will read the table and the number of rows you want to specify. As there are 5 rows, we will not be specifying the number of rows. Read.table, there was an error in the name specified. Changing read.table, you will get the warning message as always. And now if you display initial, you'll find there are 2 columns with the variables. Now how can you find the classes? There is a function called sapply. I'll tell you what it does. Let's say I define a variable called classes and use this sapply function. Again, there was a spelling mistake in initial. I'll correct that, and now you will find the classes have been applied. Now this classes, what it contains, you'll find v1 as a factor and v2 as an integer. Now, as I said you earlier, character sets most of the time in R, it automatically is treated as factors, and integers as always integers. Now you find the classes of v1 and v2. v1 is a factor and v2 is an integer. Now you can specify this call classes in while reading the table. Let's say I want to read the table much faster. Let's assume if there are more number of rows in this table, and you want to read this table. Let's say I create a table called sample table. You should be careful while using R, because R is mostly case sensitive. Read.table of sample dot text, comma, you should specify the call classes equal to classes. This classes is a variable which contains v1 as a factor and v2 as an integer. This will make much faster reading data. Ignore the warning message here, but this will help you read data much faster if your data has more number of rows. And you can also set n rows, which will limit the number of rows you want to extract from the data table. Let's say you don't want to run the analysis on the entire set of data, but you want to run it on a certain limit of data. So you don't need to extract. Let's say there are 1 lakh rows and you want to run the analysis only on 100 rows. You can specify the number of rows, and this will help you. It doesn't go with the speed of R programming, but it can reduce the memory usage. So this is just it's a mild overestimate, which is okay. And so I'll show you the next thing. Setting n rows is simple. So let's say you want to read only the top 2 rows of the sample.txt. You can use top 2. I'm creating a variable called top2, and I'm using read.table of sample.txt, comma n rows equal to 2. Now you have read only 2 rows from the table into the dataset top2. Now if you display top2, you will find only the the 2 rows being inserted into sample.txt. This can help you considerably when you want to reduce the size of the data you are inserting into. Now moving on, how to calculate the system capacity. Now, how to calculate the system capacity? So you should know a little bit about your system before working in R. When using R with larger data sets, it may stop R from running itself when the capacity is overused. You should know how much memory is available, which is the RAM, random access memory of your system, to compute exactly, not just exactly, just a rough calculation of how much memory will be needed for R programming to run, and what other applications are in use. You can just use the task manager and you can see the processes in it, and who are the other users logged into the system, and what operating system that your system uses, and is the OS 32 or 64-bit. Currently it's a 64-bit OS, that's why we are working with the 64-bit version of the R program. Now, how to compute it? There is a very small calculation regarding this memory requirements. So let's say you have a data frame with like 15 lakh rows and 120 columns. And let's say all are numeric data for simplicity. And you can just estimate how much memory will be required to store this data frame into an R data set. Let's say for a single character or a numeric or any kind of the atomic object that inserts into a data set will occupy 8 bytes. Let's say for numeric it's 8 bytes, and if you have some 15 lakh rows, so and which have 120 columns and each will have 8 bytes per numeric, so it will be 8 into 120 into 15 lakh, which will give you 144 into 10 to the power 7 bytes. So let's say there are like 220 bytes per MB, and like your data set will lead to 1.34 GB, which is approximately 1374 MB. So this will be the memory requirement for working on this set of 15 lakh rows of data. Now if you have 2 GB RAM capacity, you can directly go with it, which will be a little slower. But if you have a 4 GB RAM or more than that, this will be much faster. Moving on, we are going to move into textual formats. Now dump and deput are used in our programming, and which are very useful because the resulting textual format is editable, and in the case of corruption it is like potentially recoverable. So Unlike writing out a table or a CSV file, dump and depot or preserve the metadata. Metadata is nothing but the data about data. I mean, how the data is stored. You have a data, let's say you have same the 15 lakh rows and 120 columns. This metadata will tell you how these exist in the data set. So depot and dump are these functions which will help you write the data set into an external file. So again, this metadata should be preserved, so that another user, let's say some other user, comes in and writes a data set. He doesn't have to specify it all over again. So again, textual formats, they work much better with version control programs like Subversion or Git, which when you create open source programs, you need to specify the version and the subversion which you create. And this will be useful, to track changes between different versions meaningfully in text files. And textual formats can be longer lived. If there is corruption somewhere in the file, it is easier to fix it. Textual formats are there to the Unix philosophy. You can search for this Unix philosophy in official GNU pages, where you get Unix data about Unix philosophy and all. And the downside of textual format, it's not very space efficient. Moving on. So how to use this dput R objects to extract R objects. Let's say uh, let's say there is a R object and you want to deparse it using dput and read it back using a dget. Dget is, again, it's similar to read.table, only here the difference is you are just reading a data, that's all. Let's follow this small example. Let's create a data frame with a integer and a character. Control L, which will clear your screen. Let's create a data frame with a equal to 1, which is a numeric, and b equal to a, which is your character. Now this data frame is created. Now what does dput y tells you? So it tells you the structure of every character and the metadata associated with it. There are one numeric and one character, and here, as you can see, the metadata also gets stored in dput of y. Structure of list a equal to 1, b equal to structure 1l, and dot label equal to a. Class is a factor for a, and dot names of c. This is the metadata which will be used when you want to know about the data that is being. Here the data frame is very small, so this data doesn't make much sense, but when you have a larger data set, this will make much more sense. Now this file can be moved into, let's say, use this dput of function, and you can move y into a file called, let's say, y dot with an R extension. Now you see that there is a R file created with y, and you can open it with a notepad, and you will see that structure, the same thing, gets extracted into this So this is what deep put is useful. It gives the structure of the uh, data frame or any kind of data, and when you move into a specific file, it will help you store this information. Is useful when you create multiple versions for a program that you are creating, and this will help you track what are the changes in each of the versions. Now the same way you can move the data within y.r into a file. Let's say you want to create the same thing. New.y, using the dget function you can specify the file name and finish it. Now if you want to display new.y, you will find that 1 and a in columns a and b. So this is what dput and dget are useful for. Now moving on, what is dump? So dump is the same way as dput, but here you can use dump to deparse multiple objects and read back in using source. The same way dget works. Dget and dput always go together. The same way dump and source go together. Let's say you have a variable named x, which is, let us sample, and you have a data set y, which is the same as the data from that we created earlier, a equal to 1 comma b equal to a. Now using dump of class x comma y, I'm using two objects x comma y, and dumping into a file name. Let's say we are creating a file name, let's say data.r. You can keep it anything you want. Here I'm keeping it data.r. I'm creating a R file which will contain the C of x comma y. Two of the objects will be stored in dump. Now you will see that a file named dump.r is created, and when you open it through the notepad, you will find x is a sample and y, you'll find the structure for the data frame as well. Moving on, I press Ctrl L so that the screen gets cleared, and let's say if you use source of data.r, the file that we created now, you will find that and now if you display y, you'll get the same functions that we created, data sets that we created earlier. Moving on, so how can let's say you here you have taken your files which are saved in your local, and how can you take files which are available in the websites all over the world? So there are certain interfaces called connection interfaces. It's not specifically to the outside world. Let's say you have a database and you want to create a connection and extract the data from it. You can start doing that, and these are connection interface which helps you to connect with the database, and from that you can start extracting the data. These connections can be either to web servers or data servers. It depends on what you want to extract basically. So connections can be made to files. This is the most common, or other exotic things elsewhere. So file, it opens to a connection to a file. GZ file. GZ is a type of a compressed data file like your WinRAR or WinZip. It's opened to a connection, a file compressed with gzip, and bc the same as gz, and url you can specify whatever url you want, and it opens to a connection to a page. And even if you want, you can connect to any web page that is available, and you can read the data into it. Now moving on, file connections. Let's say you have a file which is here. You're seeing an example where you're trying to read a file. So strf file, the function, what basically the description is the name, and open blocking equal true. These are individual arguments for that function. So open, it will indicate whether what is the file actually. So R, which means read only, where W specifies whether you can, the writing permissions are not available or available in that, and A is appending, and RBWAB for reading, writing, or appending in binary mode, which is useful when you are coding Windows. And going on to connections. In general, like connections are powerful tools which will help you navigate files or any other external objects. Uh, you don't need to deal with this connection interface directly. So let's say you want to use a connection for the sample file that we created earlier. Control L, which will delete the contents of the screen. Let's say I want to create a con, and this file will help me to connect with the file sample.txt, comma r. Now you have created a connection which is R specifies only read only. So I'll show you what it does actually. Now you can create a data set data, and you can just use read.csv or anything else which will just use the connection variable. The connection variable is actually connected to the file already existed, and forget about the warning, this is for that data. And you can I forgot to close the connection. I'll do it once more. Using the connection to read, and in that I close the connection. Now the connection is closed. This is the same as read.csv of sample text. Instead we have a connection file, and you can display the data here, and you'll find that A1, B2, C3, D4, E5, and A and 1 are treated as columns here. And moving on, how to read lines of a text file. I don't have a sample for this gz file. So let's say you have a compressed file which is the format of gz, and you can just read use the function read lines just to read simply the lines of the text file and store them in a character vector using a connection con. Can read the use the gz file to read the let's say there is a file named words.gz, and you can just directly connect to that file and you can read it. This read lines will help you. The number of characters also you can specify. Here it is indicated as 10, so that only 10 of the variables or objects are read into it. So same as dput dget, we have a counterpart for read lines as well, which is called write lines, and it will takes a character vector and it writes each element one by one line at a time into a text file. Now moving on, so read lines also will be helpful to read lines from web pages. So there's a comment which indicates that it will take time. So let's say you want to read lines of a page from Wikipedia. This is the Wikipedia file, and you can use the source to find what kind of data it has. Here in the same way you can use clear the data, and you can create a connection which will connect to Wikipedia. Say connection equal to URL, which will URL will help you read from files http en.wikipedia.org, comma r, just specifies it's read only. It will take time, but it will do it. So this is connected to the wikipedia.org, and now you can use x read lines, and read lines L is capital. Now using this head of x will give you this. You can go to Wikipedia page and you can search the source for the file, and it will give you this. So this is the total overall data for Wikipedia page, which is stored in HTML XML format, and you can clear it, and you can just see head of x, which will give you the top 1 2 3 4 5 6 parameters inside the Wikipedia page. So this is the same example, and with this we'll finish about reading and writing data using multiple functions from table and from other data sets, from files, from URLs. This will be really helpful when you have external data sets and data sets within your local system which you want to do multiple analysis and you want to move the data into the R data sets. Hello people. Now we will see about debugging in R. So as a programmer, you would have known about debugging. Debugging is a process where you identify potential or the errors, the bugs that exist in your program, and it is a way of identifying the bug that exists in your program. And the way to rectify it, you have multiple ways in multiple programming languages, and today we will see about the debugging process in R. So what is debugging? Like I said, it is the process of identifying a bug. What is a bug? It is some sort of indication that something's not right with your code. It may be a error in the syntax. It may be error in the semantics. It may be errors in the declaration of variables. It can be anything. So how can you indicate there is something wrong with your code? You can use message. Message is a notification or a diagnostic message which is produced by the message function which is available in R. So you can, if there is any error, you can use this message function to indicate that something is error. You can declare a warning message, or warning is the next type of indication that something is wrong, but it will not affect the functioning of the code. It is not fatal, which means there is no way it is not going to affect the running of the program. And but warnings are meant to be taken seriously, and each should be given its considered amount of time and should be solved. And execution of the function continues generated by the warning function. And what is an error? Error is the next level to warning, which is an indication that it is a fatal problem, which means the program cannot run anymore, and the execution of the program stops, and which can be produced by the stop function. And the condition, Condition is a manually created one, or it is automatically created by R also. You can manually create it to set conditions to, when something happens, what should you do? Let's say you want to display a warning message, or you want to change the part of a code or something like that. And it's a generic concept for indicating that something unexpected can occur. So programmers have the ability to create their own conditions, and you can create your own. Moving on. So what is an example of a warning message? So as you all aware of the logarithmic function, there is log of -1 is not available, and it's not a number. So let's say what happens when you run log of -1. So this will necessarily yield NaN. So it will give you a warning message. Whenever NaN, not a number, is produced, a warning message is declared in R, which will say the warning message is NaN's produced. So this is one typical example. You can create your own warning messages, or you can use the existing automated warning messages to indicate there is something wrong with your program. Moving on. So you can use the print message to identify. Let's say you want a variable to have only variables less than 0, only greater than 0. So if someone enters a variable less than 0, you should print a message saying it is a less than 0 function. So these are simple functions written which will declare, just using the print function, you can just display a warning message, or this is just a message saying that you have to enter a variable 0. We'll see the small example where there is a function called x. Let's say we create a function called print message, which will take variables so this plus the plus symbol that comes here, which means the function is not yet complete, and you have to use a, when you put a double set bracket, the function will close. Let's use a if condition to just verify if x greater than 0, print value of x is accepted. Let's say if it is less than 0, print value of x is not accepted. Invisible hex. I'll tell you about this function later. So now this function is complete. So you have a function, let's say you want to pass a variable 1, which will say the value is accepted. Forget about the slash n, which came because I pressed enter here. So value of x is accepted if the value passed is greater than 0. Let's say I pass a variable which is less than 0, value of x is not accepted. So these are simple warning messages which can be taken into multiple levels depending upon the user who creates and the creativity level of him. So moving on, these can be used for keeping correct checks on your programs that you create. Moving on. So this is the same example I showed you. So missing value, if you are passing this NA, so where true or false is needed, this is where this invisible of x comes into play. Error in f if x greater than 0, missing value where these conditions are not available. So this is one such example. We don't have to do this in the R console. Just go through this example with you guys. Print message 2 is a function, and if the variable x is a missing value, is considered. If x greater than 0, we can print x greater than 0, and if is x less than or 0 equal to 0, you can print that, and there is a condition for x for us x is a missing value also. Moving on, the same way, so x of log of minus 1 will give you the warning message NA is produced, and print message 2 of x will give you x is a missing value. We'll finish this class with the last function that we discussed, and we will take more into debugging in detail in our next sessions. Hello, today we will be seeing about the control structures in R programming. So what exactly do you mean by control structures? These are like which will allow you to control the flow of execution of the program. For example, if you have some experience in programming, you will know about if else, for loop, while loop, repeat, break, those kind of things. So those are actually it controls the flow of the program, where it goes, how much time a module should run, those kind of things. So the common structures in the common control structures are if else condition. So these are conditional modules. For loop is like, again, it's a conditional module, it's but it loops for a fixed number of times. And while loop, again, it's same as for, but there is slight differences, I'll tell you later. And there is a control structure called repeat, which will execute in an infinite loop. And there is a break. This can be used in any loops where you want to stop the execution of the program. And next is a special type of keyword which will help you to skip an iteration of a loop. For example, if you're using a for or while statement, if you want to skip for a specific flow, you have to use the word skip. You have to use the word next, which will allow you to skip an iteration of a loop. And there is a return function which actually returns to the previous function that called the internal module. So most control structures are not used in interactive sessions, but rather when writing functions or longer expressions. Moving on, we are seeing about the control structure if. So the normal structure syntax for if is like if the condition, then do something else, do something else, then if condition, do something else if condition. The next one is your if else if condition, else if another condition, do something different, and if there is nothing else to do something different. This is your control structure. So this is a valid if else structure. I'll not be doing this in our module right now. These are simpler structures, so I'll leave it to you guys to do it on the R module. So for example, this is a valid if else structure. If x greater than 3, assign y equal to 10, else assign y equal to 0. So the next one is next another example. So if y equal to if x greater than 3, you are assigning the value of x. This is just a different way of writing the previous function. So if there is like if x is greater than 3, assign it to y, uh, and then in the loop it will have 10, else 0. So this will have, if let's say for example there is a value of x equal to 4, 10 will get assigned to y, else 0 will get assigned to y. That's all. So the else clause is actually not necessary if you are going for only one condition. So if there is one condition, you can use if condition 1 yes, and if condition 2 yes. These are just simpler things which you will not find in the previous programming languages, other programming languages. The next control structure is for. For loops actually take an iterator variable. For example, you can use iterator variables such as I, j, k, and assign its successive values from a sequence or a vector. For loops, for example, in C or C++, you will be using for loops to iterate across arrays, iterate across linked list, those kind of things. So for loops are most commonly used for iterating over elements of an object. For example, if there is a vector called I, and there is a vector with 1 to 10 variables, and you want to print all those 10 variables. This is what is given here for I in 1 to 10. You just print I. It will iterate. For the first value of I, it will print I1. For the second value, print I equal to 2, print 2. So the loop takes the I variable, and in each iteration of the loop, it will give the value 1, 2, 3, etc. up to 10, and then it exits. So here again, we are giving you an example. So for x, you have values of an array for a vector a, b, c, d, and so for I in 1 is to 4, print x of I. So this I value gets changed between 1 to 4. So for example, here 1 to 4, print x of I will give you a, b, c, d. X of I is, x of 1 is a, x of b is b, x of 3 is c, x of 4 is d. So for in I in sequence along x is again a special function in R programming, which will again it will iterate from it will follow the perfect sequence from a variable, beginning variable to the end variable. Again, you can use print letter in x. For letter in x, print letter. That is also possible. A letter will iterate from the beginning of the vector to the end of the vector. So again, the last one is our simpler one. For I in 1 is to 4, print x of I. Moving on. So nested for loops. So what are nested for loops? Like, there is a for loop and you want to write another for loop within it. So that is nested for loops. Nested for loops are most commonly used for matrices. So here you have a matrix called X, which contains 2 rows and 3 columns. So which has values 1, 2, 3, 4, 5, 6. So we have for I in sequence length of n row of x, number of rows in x. So for the first row, for the first column, second column, third column, you are printing the values, and the next row for the first column, first column, second column, third column, you will be printing the values. So you should be very careful with nesting. Actually, nesting beyond 2-3 levels is often very difficult to read or understand. As you can see, for matrices, if you only when you write it down, you will understand what happens here. But other than that, it is very difficult to understand this. Next control structure is while statement. While loops actually begins by testing a condition. So if it is true, if the condition is true, then they execute the loop body. Once the loop body is executed, the condition is tested again and so forth. For example, count less than 0. So while count less than 10, print count plus 1. So what here happens here is when the count is less than 10, you're just printing the count. So and then what happens? You are incrementing the count variable. Initially, the count starts with 0. So the next, when the variable is goes into the loop, count less than 10, it's 0, so it goes into the loop, and it is incremented. The count value becomes 1, and again it comes to the loop. Count is greater than less than 10, so again it goes into the loop and goes on till it turns 10. 10 it will go on, and after that, when count is less than 10, so if it is less than till count 9, it goes on. 9 is less than 10 will get printed, and count value will be 10. After that, when you test count, you'll the loop will not run. So while loops can potentially write in infinite loops if not written properly. Again, like you should be using it with care. You should be familiar with the conditions what you are using the while loop for. And this is an example. So we can test multiple conditions in while using while statements. Sometimes you can use multiple conditions. For example, here is it less than 5. So you are testing for two conditions here. When is it greater than 3 and is it less than or equal to 10, you're just printing is it, and you are just creating a binomial function here. I'll tell you later. So you are just assigning z equal to z plus 1, else is equal to z minus 1. So this loop goes on testing for the conditions, incrementing z values. So and the conditions are always evaluated from left to right, as most of the human languages. And then we are seeing repeat. So repeat actually creates an infinite loop. So like these are not commonly used in statistical applications, but they have their uses. the only way to exit a repeat loop is to call break. You should inside a repeat loop you should have a condition and it should call break. Otherwise, the loop might run continuously and it will take up your processor capabilities, everything. So we have a value x0, we are assigning the value 1, and we have one more variable 12, and this repeats x1, which is like log of -8, and compute estimate if absolute value of x1 minus x0 is less than 12, then break, else x0 is assigned x1 to x0. This is how the repeat works. It will break whenever you want to break the statement, you have to use the condition break. So it is a bit dangerous because there is no guarantee it will stop. Better to set a hard limit on the number of iterations. For example, in the repeat, you can just set a count variable for how many times, maximum number of times or minimum number of times it should run, and then just finish it. Whenever the loop tends to run infinite, using a count variable, you can stop the repeat function, the repeat statement. So you should set a hard limit that will be a safety measure, and then report you can whether the convergence was achieved or not. And there are like the next thing is the next and return. Next, as I told you earlier, which will be used to skip an iteration of a loop. For example, I don't want the first 20 iterations to run when I'm running the iterations from 1 to 100. I don't want 1 to 20. I want to start it from 21 to 100. So if I is less than 20, I'm just using next. So it will skip the iteration, and it will start only when 21. You can use this I less than or equal to 20 condition for any number of any kind of conditions you can create using that. And return signals that a function should exit and return a given value. Return, actually, it's it's used in functions which will just return some values to the function that calls the inner function. And control structures, I am giving you a summary of it. So we saw the control structures like if, while, and for allow you to control the flow of an OR program. Infinite loops should generally be avoided, even if they are theoretically correct, because this will take up all your and this will be running infinitely, and it will occupy all your programming. I mean your processor space and processor memory, and this will create unwanted issues in your system. And control structures mentioned here are primarily useful for writing programs. For command line interactive work, and apply functions are for the apply functions are more useful. I'll tell you about the apply functions a little bit later. We'll be seeing about functions, which form one of the most interesting characteristic of any programming language. Functions are specifically written procedures or modules which performs certain task that you assign it to. So in R programming, the keyword used to create functions is R, is function, followed by two set brackets. Directive, and are stored as R objects, just like anything else. In particular, they are R objects of class function. So you have seen like multiple vectors and characters, integers being stored as objects in R programming, and in the same way, functions are also stored as objects of class function. So this is a common syntax. F, you are assigning a function to F function and the arguments that you are passing into, and these arguments are nothing but values, variables which you want to use inside the function, and inside the function you are doing something, and your closed loop. So this is your function syntax. And functions in R are first class objects, which means you can treat them much like any other R object. Importantly, functions, you can pass functions as arguments to other functions, and functions can be nested, same as your looping statements, so that you can define any number of functions within a function. The return value of a function is the last expression in the function body to be evaluated, which means you are giving a specific task to a function. Let's say a function to add two numbers. You are passing an argument a comma b into that function, and the values, value computed inside the function a plus b, should be used, should be returned using the return statement, as you saw in the control structures. What are these function arguments? So like you have these named arguments, which potentially have like the default values. So the formal arguments are the arguments included in the function definition. Every function will have a definition which will say the number of arguments that get passed into and the nature of arguments, like is it a character that is getting passed into, or integer, or it can be anything else. So the formal function returns a list of all the formal arguments of a function. Not every function call in R makes use of all the formal arguments. Function arguments can be missing, or it might have default values. Argument matching. So argument matching, it's like these functions arguments can be matched by position or by name. So the following calls to SD are all equivalent. Let's say like there is a function my data where r norm of 100. So you have SD of my data. So the my data is passed into the function SD as a vector. So SD of x equal to my data also you can assign, or you can pass directly as SD of my data. And the next is xd of x equal to my data, wherein you are assigning a name to my data. And SD of x equal to my data comma na dot rm equal to false. Same way you can send it vice versa, SD of na dot rm equal to false, x equal to my data. Again the same way you can pass without assigning my data equal to x, SD of na dot rm dot equal to false comma my data. So it is allowed in R programming to to change the argument's position, but I would not recommend you to do that, because it will create more confusion while you are using the programming. So you can mix positional matching with matching by name. When an argument is matched by name, it is taken out of the argument list, and the remaining unnamed arguments are matched in the order that they are listed in the function definition. Args of LM function, it will give you the formula, data, subset, weights, any dot action, method equal to QR, model equal to true, x equal to false, y equal to false, QR equal to true, singular dot OK equal to true, contrast equal to null, offset, and those kind of things. So you are seeing two equivalents of the same function here. LM of data equal to my data, y approximation x, model equal to false, 1:100. Again you are passing the same function, just switching the positions of the variables here, and both are exactly correct. Now most of the time named arguments are useful on the command line when you have a long argument list, and you want to use the defaults for everything except for an argument near the end of the list. Named arguments also help if you can remember the name of the argument and not its position on the argument list. For example, you can go height and width if you are passing inside passing as arguments inside functions. You can just use keywords height comma width for getting those arguments, so that you can easily remember. Height means height, like a width means weight, same as that. So for example, plotting, you can use x comma y axis. If you are passing through the function, you can remember x equal to x and y equal to y, so you can easily remember what is what when you are passing the names as a function inside the function. So function arguments can also be partially matched, which is useful for interactive work. The order of operations when given an argument is: check for exact match of a named argument. So whenever you named the argument, this is the order of processing. So whenever you're named, the names will be first taken into consideration, and check for a partial match. If there is like the variable name, using the variable name, they will look for a partial match, and based on that, others will be formed. And the last comes your positional match, where exactly it is called for x comma y or y comma x, those kind of things. Moving on, so defining a function. So how am I defining a function here? So I have a function called f, which will be using the f assignment variable function, and I'm passing four arguments into the function a, and b equal to 1, c equal to 2, and d equal to null. I'm assigning the values b equal to 1, c equal to 2, and d equal to null inside the arguments itself. So when they get passed into the function, they will have the default values b equal to 1, c equal to 2, and d equal to null. So in addition to not specifying a default value, you can also set an argument value to null, which will automatically initialize argument that is passed into the function as null. So lazy evaluation. Arguments to functions are evaluated lazily, so they are evaluated only as needed. So if you are not using an argument that is passed into the function, it will never get evaluated because it is not needed to be evaluated. So if I'm creating a function which passes a comma b, and the function does just a square, and this function, when you're passing the variable f of 2, this function never actually uses the argument b. So calling f of 2 will not produce an error because the 2 gets smashed by the position, nothing else. And here the result will be, if you're calling f of 2, it will be 2 square, the answer will be returned as 4. But the value b, the argument b, is not used in the function, so hence there will not be any error when you are using f of 2. Another example is like f function a comma b, print a comma b. So if I'm passing f of 45, and this will give you a error in print b. So we'll see this, we'll start evaluating in the our module. So I'm creating a function f which will have function of a comma b. So this plus means you are going to the next line of the function. Here I'm printing a, print b, and I'm closing the bracket. Now the function is complete. So if I call f of 45, what happens? Argument b is missing with no default, which means the function is supposed to have two arguments a comma b, and I have called 45. Earlier we saw an example where the value b was not used inside the function. For example, here we have used print of b, but the function doesn't have the second argument. So this will give you a argument is missing error. So, and as you can see, there is the value 45 that gets printed because it goes sequential. So it prints the function. It doesn't check for the arguments first. The first thing that happens is the printing of the variable a, and then goes to the next. And when it checks for the print variable b, it notices that the argument is missing, and it gives an error. So this is what is called lazy evaluation. Like whenever it is needed, it will done. So once the function tried to evaluate print b, it had to throw an error. Again, this argument triple dot, it's called an ellipsis, indicate a variable number of arguments that are used to pass to other functions. Is often used when extending another function and you don't want to copy the entire argument list of the original function. So yeah, here you have a function called myplot, which has the arguments x comma y, type equal to L, and other arguments as well. Plot of x comma y, type equal to type comma other arguments. So generic functions use this triple dot as arguments, so that extra arguments can be passed to methods. For example, mean function of x comma etc etc etc. So use method of mean. That's it. Again, this argument is also necessary when the number of arguments passed to the function cannot be known in advance. For example, there are multiple functions in R programming like which you can use for your regular day-to-day use, and those functions you don't have to know all the arguments that are available in the function. Instead, you can just use that triple dot args of paste function of triple dot comma separation equal to null, collapse equal to null, and this can be used to identify to pass the arguments when you don't know what are the arguments that are passed. Okay, the same example is given the next. So the arguments coming after this triple dot. One catch with triple dot is that any arguments that appear after this on the argument list must be named explicitly and cannot be partially matched. So there was partial matching I mentioned earlier when the arguments are matching, but here you cannot use this partial matching, especially when you are using triple dot and followed by, especially for example here is a function of this dot 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 comma SEP equal to, you are assigning the names SEP equal to nothing and collapse equal to null. So again paste of a comma b separate equal to separator equal to colon, so it give you a is to b. The same way again separator equal to b. So it proceeds on with this function. So you should be very careful when you are using this double dot, because when you are passing multiple arguments after this dot 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 symbol, you will find that the function will look for variables that have the names that get exactly matched. So with this we conclude functions in our programming. Now we'll see about scoping rules in R programming, and what are they and what exactly are they used for. So how does R know which value to assign to which symbol? When I type, let's say lm a function of x star x. So how does R know what value to assign to the symbol lm? Why doesn't it give it the value of lm that is in the stats package? So there are like multiple stats package where this lm variable is declared and used. So I'll tell you later how do you bind values to a particular symbol. So when R tries to bind a value to a symbol, when it tries to assign a value to a symbol, it searches through a series of environments to find the appropriate value. When you are working on the command line and you need to retrieve the value of an R object, the order is roughly like it searches for the entire global environment for a symbol name matching the one requested. For example, the lm that is used in the previous program, it will be searched in the entire global environment before matching the one requested. And again, next thing is a search the namespaces of each of the packages on the search list. Namespaces are just list of all the variables or functions used in a particular package. It will be given in the search list. So again, you can use the search function to extract the search list. For example, if you use the I'll show it in the R module. So if you use search, it will give you the packages available in R programming. .global env, package stats, package graphics, package GR devices, package utils, package datasets, package methods, autoloads, and package base. So these are your packages available in this search list. So this list will be searched whenever you are assigning a value to a symbol, and this symbols will be searched in the namespaces and this search list. So we are seeing this binding values to a symbol. The global environment or the user's workspace is always the first element of the search list, and the base package is always the last. The order of the packages on the search list definitely matters. As you can see, it starts with the .global environment and package base at the end. So every search list will start from here global environment to package base, and the search of each namespace will start from this to this. So that's the reason the order of the packages on the search list matters. So users can configure which packages get loaded on startup. So whenever you want to whenever you are working on R and you want to start using this is nothing if you know C programming or C++, this is same as using include the library files, include variable in C++. So you cannot assume that there will be a set of list packages available. So when a user loads a package, With library, the namespace of that package gets put in position 2 of the search list by default, and everything else gets shifted down the list. So for example, you are loading a package from the library, so it will put next to the global environment search list, and position 2 of the search list will be occupied by the namespace that you are using in your program, and everything else gets shifted down the list. And you can note that R programming has separate namespaces for functions and non-functions. So it is possible to have an object named C and a function named C. So you can have a the naming can be same, but the characteristics can be, it can be either an object or it can be a function, and it can be stored in multiple locations. For example, if you have an object named C, it will get stored in others, but for functions it will get stored in methods. What are the scoping rules? So the scoping rules of R are the main feature that makes them different from the original S language. So they determine like how a value is associated with the free variable in a function. So they use R programming uses lexical scoping or static scoping. Common alternative is dynamic scoping, which I'll explain you later. Related to the scoping rules is how R uses the search list to bind a value to a symbol. So lexical scoping turns out to be particularly useful for simplifying statistical computations. So you have a function called f which has arguments x comma y, and it performs the following things: x square plus y divided by z. So notice that z is not available in the argument list. So this function has like two formal arguments x and y. In the body of the function there is another symbol z. So in this case you can call that z as a free variable. The scoping rules of a language determine how values are assigned to free variables. Like the scoping rules are nothing but, it determines the scope of each and every variable. Where does z actually come from? Is it within the function? For example, the variables x comma y, the scope is within this function. Free variables are not formal arguments. You cannot put them in formal arguments, and are not local variables. Which are local variables are here. The local variables are x and y, which are assigned inside the function body. So z is actually a free variable which will be declared elsewhere apart from the function. So it will be stored in some kind of objects or function depending on what it is. So lexical scoping in R, it means that the values of free variables are searched for in the environment in which the function was defined. We'll see the example that we saw earlier. So let's say I'm defining a variable called z. It's done. So now I'm creating a function called f function of a comma b, and here I am declaring a plus b plus z, and I'm closing the function. Now this function has two variables a and b. So if I am passing f of 2 comma 3, it will give me 10 because a plus b is available within the function. The scope is within the function, and the value z, it is declared from z equal to 5. This z will be stored in any of the packages above, the base package mostly. So the environment variables it will be in the environment. Lexical scoping in R, it means that the values of free variables are searched for in the environment in which the function was defined. What is actually an environment? It is a collection of symbol comma value pairs, that is x is a symbol and 3.14 might be its value. For example, in this example, z is the variable and phi is z is the symbol and phi is the value assigned to it. So this will be assigned to the global environment. So every environment, it will have a parent environment. It is possible for an environment to have multiple children. For example, every environment that will created in the R package will possibly have the global environment as their mother package, parent environment. The only environment without a parent is the empty environment, which doesn't have any symbols or values associated with it. A function plus an environment is equal to a closure or a function closure. So this is called as the completeness of the function. A function plus an environment will give you the function closure. So how does the value of a free variable is searched? Here I declared z equal to 5. How does this getting searched and brought into the function? So if the value of a symbol is not found in the environment in which the function was defined, then the search is continued in the parent environment. So the value of z is actually searched inside the function or where it is being called for, but there is no assignment to z within the function, so it is searched in the parent environment, which is the global environment package. So then the search is continued in the parent environment. The search continues down the sequence of a parent environment until we hit the top level environment. This is usually the global environment workspace or the namespace of a package. So when I have declared z equal to 5 and use this function, what if a variable is not at all declared or within any kind of environment variable, then it will return an error saying that variable is not available elsewhere. So after the top level environment, the search continues down the search list until we hit the empty environment. Once the search reaches the empty environment, there you will decide that the variable is not available. So if a value for a given symbol cannot be found once the empty environment is arrived at, then you will get an error saying that the value is not available, that the symbol is not available exactly. Yeah. So why does this matter? Typically, a function is defined in the global environment so that the value for free variables are just found in the user's workspace. Again, this behavior is logical for most people, and it is usually the best thing or the right thing to do. However, in R programming, you can have functions defined inside other functions. They're like in C++, you have like you can the main function contains other functions. That is the only thing that can happen. But in R programming, you can have any number of functions within any function. So C doesn't allow you to do this. Now things start get a little interesting. In this case, the environment in which a function is defined is the body of another function. So for example, if I have a function A and I define the function B within the function A, uh, so it is the body of another function. So you are defining a function within the body of function A. So that's where things get a little interesting. So I have a function make.power where I have assigned function of n. Within that, I create one more function which is just nothing but power. POW equal to function of x, and within that function you just raise x power n. So and you return pow. What is the value of pow you return? For example, we'll see the example. We'll put this example in our module. Control L. I'm clearing the screen. Make dot power is a function I'm defining, which will have a function of n. So again, in this function, I'm defining one more function, which is pow, is a function of x, and within that, I'm raising x to the power n, and I'm closing the power function, and I'm just throwing out the function, and this is completed. So this function is completed now. So I want to calculate a cube, so I'm assigning this cube to make dot power of 3. So if I use cube of 3, give me 27. So there are two values, x comma x passed in, x comma n, x is equal to 3, n equal to 3. So that's the reason you're getting function. So this is where lexical scoping comes into play, and exploring a function closure. Exploring a function closure. So what's in a function's environment? So when you type the command ls of environment cube, you get n power. So you basically get what are the parameters that being used by a certain function or a method when used in an environment. So you can also use get of n comma environment of cube. When you use that, you will get 3, the value of n that we normally use. So the same way, if you apply for ls of environment square, you'll get n comma power, the same variables. But when you get the values of n that is being used, get of n comma environment of square, then you will get 2. As in the function square uses the value 2, as in square uses exponential of 2, and cube it will be exponential of 3. Moving on, you'll see about lexical versus dynamic scoping. So let's have a function. We have assigned y as 10, and we have a function f wherein the function of x, y is assigned a value 2, and y square plus gx inside the function g of x. Now the g of x function is called, and we have a function g wherein function of x, x star y. So what really happens when we call f of 3? So what really happens is, even though the variable y is declared outside the function x, the variable that is declared inside the function y equal to 2 will be used for this computation. So basically what happens is, it will be y square, which means 2 square, plus g of 3. Again 3 will be passed on to this, so 3 star y. And what happens is, 3 is multiplied by this y value will be taken from the value of y equal to 10, because this y starts within this bracket and ends within this bracket. The value of y equal to 2 will be within this brackets only. It's local. So outside the function, the value of y will be 10, which will be called for this function. So when x star y is called, this will be called. So when we call f of 3, so g of 3 will be called. So 3 star 10, 30, 30 plus 4, we will get 34. That is the result that we get here. Moving on, with lexical scoping, the value of y in the function g is looked up in the environment in which the function was defined. So we are still going on with the previous example. In this case, the global environment, so the value of y is 10. So with the dynamic scoping, so dynamic scoping is when the value of y is looked up in the environment from which the function was called, sometimes referred to as the calling environment. In R, the calling environment is known as the parent frame, so the value of y would be 2. So moving on, uh, when a function is defined in the global environment and is subsequently called from the global environment, then the defining environment and the calling environments are the same. This can sometimes give the appearance of dynamic scoping. So we'll consider an example. So we'll have a function called g, which takes the parameter x, and in this we have a parameter called a, which is defined inside a equal to 3, and it performs the computation x plus a plus y. Now as you can see, when you call g of 2, what happens? The function x is called function of 2, and inside you'll have value of 3, a is there, value of x is there, but value of y, it is not defined anywhere. So as you can see, we'll get an error in g of 2, object y not found. So let's say if I declare outside then y equal to 3, this is a global value which will be used in any function that calls a parameter y. So now if you call again g of 2, you will get x plus y, which is 3 plus 2 plus 3, you'll get 8. So that clearly defines, explaining the scope of each variable is defined in your programming. So moving on, uh, what are the other languages that support lexical scoping? There are like multiple languages. The common Lisp language, all languages converge to Lisp, Python, Perl, and Scheme. All these languages support lexical scoping. So what are the consequences of lexical scoping? In R, all objects must be stored in memory. All functions must carry a pointer to their respective defining environments, which could be anywhere. So in S+, free variables are always looked up in the global workspace. So everything can be stored on the disk because the defining environment of all functions is the same, because the defining environment here is the global workspace for S+. So here all the variables can be easily stored in a disk. So what are the applications of this lexical scoping? So the first thing that comes into anyone's mind is optimization. So why is any of this information useful? Optimization routines in R, like optim, NLM, and optimize, they require you to pass a function whose argument is a vector of parameters. Example, a log likelihood. So, however, an object function might depend on a host of other things besides its parameters, like the data that it's using. So when writing software which does optimization, it may be desirable to allow the user to hold certain parameters fixed. So this is one of the biggest areas where lexical scoping is used. So these are examples for normal likelihood. So we are writing a constructor function. So a function make dot negative log likelihood, which is shorted as neg log like, is a function which has the data and where a boolean variable fixed equal to c false comma false. So within this you'll have params is fixed, you'll have an inner variable called params where you pass in the fixed boolean variable fixed into params, and you create one more function of p, in which, so you will have params of not fixed equal to in which params are not fixed, you are passing p. So again there is two variables, mu equal to params of 1 and sigma equal to params of 2. So this is how you create a normal likelihood. We can try this on R programming. You will be able to plot it. As soon as we finish the course of plotting, we'll have a good idea of how to plot a likelihood of normal curve. So wherein you have a equal to zero point 0.5 minus zero point 0.5 length into length of data into log of 2 into pi into sigma square. The same way you define a variable called b, where you have minus of 0.5 into sum of data minus mu square by sigma square. So and minus of a plus b. So this is optimizing a normal likelihood function. So here optimization functions in R minimize the function. So you need to use the negative likelihood. So when you set a seed, what happens is there is a random normal distribution function, which will create 100 random variables with mean equal to 1 and standard deviation equal to 2. So when you set seed, it will remember what are the random variables that are created, random integers or numbers that are created. So NLL is equal to make dot neg log like of normals. So you have the normal variables passed into the negative likelihood. So when you call NNL again, the function will be called, and this environment NNL data fixed params will show up, and this environment will be plotted as a normal likelihood. So how do you plot this likelihood? I'll give a small example here. So you have the NL variable here, make dot neglog like of normals comma C of 1 comma false, and we have a variable called X which will be used for plotting, where we have a sequence 1.7 comma 1.9 length equal to 100, and y equal to s apply of x comma NLL. Now if you plot of x comma exponential of minus of y minus min of y comma type L, this will give you a plotting graph of the negative likelihood. The same way you can just changing the values of C of false comma 2 and sequence from 0.5 to 1.5, you'll get same kind of negative likelihood with the values 0.5 to 1.5. So that's how you use the negative likelihood. So now coming to the summary of lexical scoping. So objective functions can be built which contain all of the necessary data for evaluating the function. So you don't have to carry around long argument list which are useful for interactive and exploratory work, and code can be simplified and cleaned up. So that's it about lexical scoping. And in case of if you need any reference, you can use books by the book by Robert Gentleman and Ross Ihaka, Lexical Scope and Statistical Computing. So with this, we finish our lexical scoping uh, presentation. In this session, we'll see about loop functions. So we'll explain you what is looping, and here we are seeing about looping on the command line of R programming. So here we know about for loops, while loops and all. So if there are any simple ways to use those in the command line, it will be really useful as a programmer. So writing for while loops is useful when programming, but not particularly easy when working interactively on the command line. So there are some functions which implement looping to make life easier. For example, like in R programming especially, you have functions called lapply, sapply, apply, tapply, and mapply. So what are these basic functions? What do these basic functions do? We have lapply. What lapply does is it loops over a list and evaluates a function and each of the element. And what is sapply? Same as lapply, it loops over a list and evaluate a function on each element, but it tries to simplify the result. So I'll give you examples and it will give you a clear-cut idea of what lapply and sapply are. So what is apply? So apply is a function over the margins of an array, and tapply is apply a functions over subsets of a mapply, multivariate version of lapply. So these are the basic for apply functions, looping functions. So an auxiliary function split is also useful, particularly in conjunction with lapply. So I'll tell you about this function in detail in the next session. This function is called split, and this does the it's particularly works in conjunction with lapply. So what is lapply? So lapply, it basically takes three arguments: a list x, a function, or the name of the function, fun, and other arguments via its ellipsis argument. If x is not a list, it will be coerced to a list using as dot list. So we have seen about the coercion process earlier. So if x is not a list, it will be coerced to a list using as dot list. So now we'll see the what is the functional attributes of lapply. So lapply, the function of x comma fun comma ellipsis. So fun is nothing but match dot fun of fun. It matches with the function which is being passed into, and if not dot is vector of x or is dot object of x. So if the argument passed is not a list, then the conversion happens in the next step, where you have x equal to as dot list of x. So when it is not a list, it is converted into a list. And dot internal of lapply comma x comma function. This is where the function is being called. So this actual looping, it happens internally in C code, but you don't have to worry about that. lapply, using lapply will solve you that purpose. So what is the output of lapply? So lapply, it always returns a list regardless of the class of the input. let's say you have a list X of list A 1 to 5, B R norm of term random normal variables of 10. So when you apply L apply, so you'll get X comma mean. So it will apply to every list that is being passed to. For example, it will you are passing two lists A equal to 1 to 5, B equal to 10 variables. It will compute the mean for each of the elements of X. We will see this in our R programming module. So here we'll see have a list of A equal to 1 to 5 comma R norm B equal to R norm of 10. Now the X is created. If you print X, you will see 1 2 3 4 5 and random variables with mean equal to 0. Now what if I apply L apply function to this, and when I pass X and I want to calculate the mean for each of the elements of X. Now this will give me A $A, which is the first element, the mean of 1 2 3 4 5, which is 3, and mean of these 10 elements, which is 0.584092. So this is the use of lapply. So when you have like multiple elements in the list, for each of the elements is this lapply works as a for loop and performs the function mean in each of the elements. So now we have got the same answer. The answer is different here because the random variables might be different in the earlier cases. Again, we have a list of 1 to 4 and R norm of 10, R norm of 20 comma mean equal to 1, R norm of 100 comma mean equal to 5. When you apply the lapply of X comma mean here, for each of the elements, again the function is applied and you will get the mean for each of the variables. So this is the use of lapply. So you can run the for loop in the command line itself. Again, we are seeing one more example for lapply where you are trying to create a uniform distribution for the values inside X. We have X equal to 1 to 4 and you are applying the function or uniform distribution of lapply X comma or unif. So with this function you'll get the random distribution, uniform distribution for the values 1 to 4. You can see the value is 0.262 ranging from 0.71. So this is how the lapply function works. Again, we will see one more example. So where we have X equal to 1 to 4. Maybe we can see this example in our module. So here we are trying to create a uniform distribution where we'll have minimum is 0 and maximum equal to 10. So it will not start from the negative. The minimum starts from 0 only. So let's assume we have X equal to 1 to 4, and now when you apply the lapply function X comma R unif, the function name, and I'm passing through the ellipsis parameters where min equal to 0 comma max equal to 10. Now when I run this, you will get the corresponding values. Every value will be as a random distribution between 0 to 10. Now moving on, lapply and friends, they make heavy use of anonymous functions. So when you have you can create multiple functions, and when you want the function to run over a matrix or each and every element of the list, it will run. Let's say I'm creating a matrix where a list we have the basic elements of the list as two matrices. The first is a matrix of 1 to 4 and 2 comma 2. The number of rows is 2, number of columns is 2, and here we create a matrix where 1 to 6, the number of rows is 3 and the number of columns is 2. So when I create this, you will find the matrix to be 1 2 3 4 and 1 2 3 4 5 6. So what do you want to do with this lapply? So I'm I'm creating an anonymous function which extracts only the first column of the table of the matrix. So I'm creating a function called function of ELT, and this ELT function gives the first column comma 1, which means the row is empty and the column is 1. So if I take this column, this 1 2 and 1 2 3, I'm trying to extract this alone from the data. So this is an anonymous function for extracting the first column for each matrix. So I'm extracting 1 2 and 1 2 3 using the lapply function, and I'm defining the function in the within the lapply function itself. So moving on, we are coming to the part of sapply. So sapply, what it does, it will try to simplify the result of lapply if possible. So what do you basically mean by simplification? So let's say lapply normally returns a list. So if the result is a list where every element is length 1, so what is the point of having a list when you have all elements of length 1? So then a simple vector is sufficient. So that is what lapply basically does. So if the result is a list where every element is length 1, then a vector is returned. So if the result is a list where every element is a vector of the same length, so it is greater than 1, then a matrix is returned. So this sapply is a simplification function which works on the lapply values. So if it cannot figure things out, again normally as a list is returned. Moving on, we are seeing an example here. This example I think we saw earlier in the examples itself. So we have a list uh, created as called X, which has the values A 1 to 4 and B random normal variables of 10, C random normal variables of 20 and the mean is 1, and D equal to random normal variables of 100 comma 5. So when I apply the lapply x comma mean, you'll find 2.5, random normal variable 10, 20 comma 1. About all these variables you'll be given the mean function. So what does so the now as you can see, the result is a list. You'll have $A, $B, $C, $D, each points to a particular mean value, and this forms a, we have only one element per inside the element. So that's the reason it's giving us a list, because we are using a. Now what if I use sapply function? Now if I use sapply of x comma mean, I'll get a single vector wherein I have the values of 2.5, 0.06 about for each of the elements in the list. So now warning message is displayed in main.default of x. Argument is not numeric or logical, and returning NA. Now we'll see about the apply. Apply, this is used to evaluate a function, often an anonymous one, over the margins of an array. So it is most often used to apply a function to the rows or columns of a matrix. So it can be used with general arrays. Example, you can take the average of an array of matrices. It is not really faster than writing a loop, but it works in one line. That's a simplicity of apply. So what does str of apply give you? It is a function which takes x, the margin, and a function. So basically the element, the list where the function is being applied, and you have an extra parameter called margin. So what is that? So x is an array, and margin, it is an integer vector indicating which margins should be retained. So function is the function to be applied, and ellipsis as always for the other arguments to be passed to the function. Now, so here you have a matrix of random normal variables 200, number of rows equal to 20, and number of columns equal to 10. Now when you apply the function apply, so you have x, 2, and mean. Now you are specifying that the margin is 2. So basically you'll find only 10 variables, 10 for each of the 20 columns. So that's the reason apply is giving this. And when I use apply of x comma 1 comma sum, now I'm taking margins to be read as 1. That's the reason I'm getting 20 outputs for this, for each of the rows. So this is where apply is much more useful. You can try to retain the specific margins that you want from the data. So when you want to perform column rows, column sums and row sums and means in a matrix, you can always use apply. For example, for sums and means of matrix dimensions, we have some shortcuts. Row sums equal to apply of x comma 1 comma sum, so it will give you first row and it applies the function sum. And row means same way, the function is mean instead of sum. And when you want the column sums, you can use apply of x comma 2 comma sum, which means the column will be considered. So call means of apply of x comma 2 comma mean. So the shortcut functions are much faster, but you won't notice unless you are using a large matrix. So other ways to apply, so if you have quantiles of the rows of the matrix you want to get, so quantiles are normally 25, 50 and 75 and complete. So this is how the quantiles are defined: 1 to 25, 25 to 50, 50 to 75, 75 to 100. So when you apply to the range of the quantiles, so apply x comma 1 comma quantile comma probs of equal to c of 0.25 comma 0.75. When you apply this, you will get the following result. So you'll get for result for each and every quantile: 1 2 3 4 5 6 7 8 9 10 11, each of the quantile you will get the result. So this is how apply can be useful to you. So the average matrix in an array, so A is an array where random normal of 2 into 2 into 10 comma c of 2 comma 2 comma 10. When you apply, you want to get c of 1 comma 2 and you want to get the mean for those, you can use this and you will get the row means. And same way, if you want to get row means of a comma dims of 2, you'll get the same values, exact same values as this, which means you are the apply of c comma 1 comma 2, which means the first row. It is a basic, the same function is followed by row means and apply. So that is the way apply is used. Now we'll see the part 2 of loop functions, where in the part 1 we saw about sapply, lapply and apply. Now in the loop functions part 2 we'll see some more the apply functions. So here we have a function called tapply. So what does tapply basically do? So tapply is used to apply a function over subsets of a vector. So basically we saw about lapply, where you the apply function applies for each element of the list, and sapply function where the result set is simplified, and the apply function where you apply the functions over the margins of the data. But what does tapply do is, like, let's say you have 10 elements and I want to specifically apply a function to 10 or 3 to 5 elements. Then I can use this tapply function, which will extract a subset from the existing list, and then the function will be applied over it. So the reason why it is called tapply is unknown to any of us. And when we see the function structure of tapply, so using the function str of tapply, we'll have x index function equal to null and simplify equal to true. So what is this actually? The x is the vector that is being passed on to. Index is a factor or a list of factors, or else they are caused to factors. And fun is the function to be applied, and ellipsis as always contains the arguments that should be passed to fun. Simplify equal to true or false. Do you want to simplify the result or do you don't want to? So tapply basically function, like functions like the sapply here. So when you want to take specific group means, you can always go for this tapply function. So let's say you have a element called x, where you have the random normal distribution of 10, or uniform distribution of 10, random normal distribution of 10 comma 1, where the mean is 1 and there are 10 variables. So when I apply a function, when I create a subset wherein the f is a subset and I'm exacting gl of 3 comma 10. So now when I use f, you'll have the values. This is not a subset actually, this is having values. I'm trying to repeat 3 10 times, so till 3 10 times. So 1 you'll have 10 times, 2 you'll have 10 times, 3 you'll have 10 times. So this is the function on f, this is the level for, and you have this factor, you'll have 3 levels, 1 2 1 3. So now if I want to apply the tapply function with x comma this factor and mean, so you'll have 3 levels and you'll get correspondingly 3 levels of mean. So you've correspondingly applied this factor over x, function over x, and you created, you found out the mean. If I do tapply without simplification, what does happen? So I'm taking the same example here. So I want to take group means, without simplification. So tapply of x comma f mean comma simplicity equal to false. When I set this, I'll get the without simplification result, wherein I'll get the list again as the result set. So finding group ranges. So same way of applying mean, you can apply range, wherein it will give you the range of each of the levels of the data. For example, when I use the tapply of x comma f comma range, I'll get the range of values in the function f. So initially it was random normal to 10, random uniform of 10, random uniform of 10 comma 1. You'll get the range for each of the elements in that. So this is where tapply correspondingly you create subsets, 3 different subsets, and try to find the range or mean or any kind of function that you want to calculate. So moving on, as I told you earlier, I will tell you about a function, specific function called split. What the split does, split, it takes a vector or other objects and it splits it into groups determined by a factor or a list of factors. So doing a str of split, it will structure of split, it will tell you it's a function which contains variables, parameters x, f, drop equal to false. So x is the factor, vector or the list or the data frame that is being passed on, and f is the factor or corresponds to 1 or a list of factors. Now drop, it indicates whether empty factors levels it should be dropped or should be considered. So here you have x, you have a list wherein the first is a random normal distribution of 10 variables, random uniform distribution of 10 variables, random normal of 10 to 10 variables where 1. So it's the same as a previous function example which we saw for tapply. Now when I apply the function f, which repeats 10 times, 1 to 3 10 times. So when I use the function f to split x comma f, it will specifically split the list into 3 different 3 different subsets and calculates the function over it. So that's the reason you'll get a result like this. But here we don't go for simplification, and hence you are getting a list as the expected result for the split function. So a common idiom is, in R programming is to use split followed by an lapply. So lapply, you can use split of x comma f comma mean. So it will give you practically the same result. It will consider the 3 of the subsets, and it uses a split to create that subset, and lapply applies the mean function over it, and you will hence get for each of the subset you'll get the mean for each of the subsets. So this is an example from an internet data. I created a data set, and I brought in using the library function, library of data sets, and this is a function that gives this air quality, and when I take head of air quality, it will give me the columns available in the air quality, ozone, solar.or, wind, temperature, month and day. Now this is a typical data frame wherein I want to perform certain specific things. So how do I split this data frame? So S equal to split of air quality comma air quality of month. So I want to split the air quality by month wise. So how do I do that? Now if I use lapply comma lapply of S function, the split function comma function of x, and I calculate call means of x in that function of x, x c of ozone comma solar comma r wind. So now you'll get the same ozone, solar, r, wind for each of the months. For example, month 5, ozone, solar, wind, you'll get the same values. Ozone, solar, wind for 6, ozone, solar, wind for 7, etc. So this is how you split a data frame using split function. Now moving on, splitting a data frame using sapply function, same split is called from S function of x, call means of x, c of ozone, solar, wind. So same, pretty much the same thing. You are viewing in a different for 5, 6, 7, 8, 9. You are viewing it in a separate format. So same way, if I use, if I want to remove this, NA values from this data, because most of the data points will be NA, and you don't want to consider these NA values. So what you can do is, S apply of S comma function of x, call means of x comma c of ozone, solar, dot wind, and I use a specific thing called NA dot rm equal to true. What happens is it removes NA values, and I have set it as true so that it can be removed. So now you'll find all the NAs are removed and replaced with the remaining attributes. So how to split the data on more than one level? So let's say you have a random distribution set passed on to x, and you have f1 equal to gl of 2 comma 5 and f2 equal to gl of 5 comma 2. Basically what it does is, gl is the function which will give you, basically it repeats 1 to 2 5 times, and here 1 to 5 2 times. So you'll have f1 1 for 5 times, 2 2 times. This is, you'll have this is factors actually. So it will have levels 1 comma 2. Same way for here you'll have levels, 5 levels, 1 2 3 4 5, and everything will be repeated twice. So now if I create an interaction set of between these two factors, interaction of f1 comma f2, you will have 1.1 1.1 1.2 1.2, basically the all possible combination, and you will have 10 levels, basically 5 into 2 equal to 10. So you'll have basically 10 levels of data while splitting this. So now sometimes what happens, interactions can also create empty levels. So when I use str of split of x comma list of f1 comma f2, you will have num of 1 to 2 and num 0. You will find all these empty levels, num of 0 here, num of 0 here, 1.4, num of 0 here, num of 0 here. Basically there are 4 empty levels when you use splitting on more than one level. Now if I want to the empty levels to be dropped, what can I do? I basically explained you in the initially explained you while telling the structure of split. You have a parameter called drop, which when set to true it will remove all the empty levels, empty factor levels that can be dropped. Now the list of 10 becomes list of 6 once you apply the condition drop equal to true. Now there is one more apply function that we saw earlier, that we are supposed to see earlier. Like this is mapply. What is mapply is that it is a multivariate apply function. So it is a multivariate apply of sorts which applies a function in parallel over a set of arguments. So when you apply the structure, when you get the structure of mapply, so this is a function which takes the function itself, the ellipsis, more, which means more arguments, and equal to null, simplify equal to true, use dot name equal to true. So the fun is the function to apply. It contains more the arguments to apply over, and more arguments is simply the list of other arguments that pass to be the function, and simplify indicates whether the result should be simplified. That's it. So now what does mapply do is like the following is, it is tedious to type. So if I want to create repeat list of 1 to 4, I want to repeat 1 4 times, I want to repeat 2 3 times, I want to repeat 3 2 times, and repeat 4 2 times. I have to use the function repeat, and in that I have to create the list. So this when it goes on and on, it is a tedious process. So what you can do is, like, I can use the function, what was the function to be applied, and use the mapply here to pass the rep function. Repeat is the function, and 1 to 4 to 4 to 1. So what basically happens is, for each of this element here, for 1 here it takes 4, for 2 here it will take 3, for 3 here it will take 2, and 1 here, 4 here it will take 1. So a rep of 4 comma 1, rep of 1 comma 4, rep of 2 comma 3, rep of 3 comma 2, rep of 4 comma 1. That is how the function works. So this, it is applying a multivariate function here, and hence it is like very useful. So how to vectorize a function? So let's say there is a function called noise, wherein function n comma mean comma sd takes n number of elements, mean and sd. So what it does, it creates a random normal distribution of n comma mean comma sd. That's what it does. It's a simple function. Just I'm trying to create some noise, that's all. So if I use noise of 5 comma 1 comma 2, you'll get the same thing. So now if I use noise of 1 to 5 comma 1 to 5 comma 2, I'll get the same values, but it will consider all these values into the consideration. Now with this instant vectorization, vectorization we were initially doing by creating the noise of 1 to 5 to 1 to 5 to 2. Now if I use the mapply here, noise of 1 to 5 comma 1 to 5 2, you will get the values here are converged together, but here you will get the exact values to be precise in the data. So it is the same, it is the same as list of noise of 1 comma 1 comma 2, noise of 2 comma 2 comma 2, noise of 3 comma 2. So basically the repeat function is used simplified using mapply here, noise of 1 to 5 to 1 to 5 2. It will consider 1 comma 1 comma 2, 1 comma 2 comma 2 comma 2, 3 comma 3 comma 2. So that's what is expanded here, and those, for all those values the noise will be created. That's it. With this we'll finish the list of looping functions. Now we'll see about simulation in this slide. So what is simulations in that? We were seeing about some random normal distributions, random uniform distributions, all those things. So now what we can do is, like, we can generate random numbers using simple steps. So there are functions for probability distributions in R. So those functions are called R norm, generate random normal variates with a given mean and standard deviation. D norm, evaluate the normal probability density with a given mean, so ST, at a point or a vector of points. P norm is evaluate the cumulative distribution function, form a normal distribution. And R poise is generate random Poisson variates with a given rate. Now we'll see about those in detail. And probability distribution functions usually have 4 functions associated with them. The functions are prefixed with the D for density, R for random number generation, P for cumulative distribution, Q for quantile function. Now working with the normal distributions, they require using these 4 functions, d norm of x comma mean equal to 0, sd equal to 1 comma log equal to false. Same way, p norm of q comma mean equal to 0, sd equal to 1, lower dot tail equal to true, log dot p equal to false. Q norm of p comma mean equal to 0, sd equal to 1, lower dot tail equal to true, log dot p equal to false. R norm of n comma mean equal to 0, sd equal to 1. So this is how you can work with normal distributions using these 4 functions. Now how to generate random normal variates. I'll show these examples in our module. So if I create R norm of 10, you'll see just it distributes the random normal distribution of 10 variables with mean equal to 0. So this is what it does. So I can assign this to x, or I can do same thing. So now if I want to create R norm of 10 comma 20 comma 2, basically what I mean here is that I want to have 10 random normal variables with 20 as the mean and 2 as the standard deviation. Now if I create this, you will find that with 2 standard deviation you will find the values of random normal variates. Now same way, if I see let's say let us think like I'm assuming assigning the random normal variates to x. Now if I see summary of x, so you'll have the minimum value is 16.31, first quartile is 19.06, median is 20.11, mean is 20.08, third quartile is 21.43, maximum is 22.37. Now this is how we use random normal distributions. Moving on, so how to set seed. What basically setting seed means is that you can setting the random number seed with set dot seed ensures reproducibility, which means when you use set seed, these are random numbers. So when you generate random numbers, these random numbers are every time you use the function, the values of the random numbers, it is random, so hence it changes. So now if you want to remember particular random normal distribution, you have to set seed, so that the language R, it takes the effort to store these values of these random normal 5 variables. So for example, if I set dot seed of 1, now if I create R norm of 5, you'll have these values. Now if I use R norm of 5, you will see that the values have changed. So what if I want to retain the values? Now if I want to retain the values, what I have to use is set dot seed of 1. So for 1, the seed has been stored. So now if I use R norm of 5, hence I will get the same values that are being stored when I use set dot seed of 1. So that's the reason we need set dot seed. So whenever you perform simulations, you have to be careful when the values are getting lost. So hence you need to use seeds to store the random values in case it gets lost in the data. So it is always recommended to set the random number seed when conducting a simulation. So now we'll see about generating random numbers. It is generating Poisson data. So what is Poisson data? Is basically it's a level of Poisson distribution. It's the same as this is a Poisson distribution, and the variables will be variates will be distributed in the follows the Poisson distribution. So now as you can see, these are, if you plot in the graph, you'll get the Poisson distribution. So for example, you can do R Poisson of 10, 2. Same way you can go ahead with like all R Poisson of 10, 20, where you get the values 20, 11, 21, 20, etc, etc. Now if I want to create a cumulative distribution, what will happen is if I want to create P Poisson of 2, 1, then I'll get this. So which is basically nothing but the probability of x less than or equal to 2 here. So here it is probability of x less than or equal to 1. So probability of same way P Poisson of 4, 2, probability of x less than or equal to 4, which is the mean here, and again probability of x less than or equal to 6 is 0.9954662. So this is how you generate Poisson data variates from the using the functions. Now, how to generate random numbers from a linear model? Suppose we want to simulate from the following linear model: y equal to 0 plus 1x plus, where n of 0 to 22, assume x n of 0 to 12, 0 equal to o equal to 0 to 5, 1 equal to 2. So now we can proceed with setting dot seed of 20, and x as random normal of 10, 100, and e as random normal of 100, 0, 2, and y equal to 0.5 plus 2 into x plus e This is the linear model that we are trying to create. So if you create, if you use summary of y, I've used the for e and x, I've used a random number of 100 and random number of 100 where the standard deviation is 2. So this is why how I've created the linear model. So now with the minimum value is 6.40. This value might change based on the random normal variates. Minus 6.4080, minus 1.5400 is the first quartile. Median is 0.686789, mean is 0.6893, and your third quartile is 2.9300. I mean, which is the second quartile is the mean, and maximum is 6.5050. Now if you plot x comma y, you will get a linear model with the function y equal to 0.5 plus 2 into x plus e. Now what if x is a binary? So I can use a binomial distribution, like you can set the seed. I'm setting the seed here. You can name any number of integer in this, which basically sets the seed. So set dot seed of 10. Now I have a x, which is the random binomial variates 100, mean equal to 1, and standard deviation equal to 0.5. Now if I have E is the error or the noise, where the random normal variates is 100 comma 0 is the mean, 2 is the standard deviation. Now the function y is defined by the linear model y is defined by 0.5 plus 2x plus e. So the only difference between the previous one and here is that I've used a binomial variates here. So when I use summary of y, you will get the values. The minimum values, again, it might change based on the binomial variates and our normal variates here. Minimum is 0.3 minus 0.3490. First quartile is minus 0.1409. Median is 1.5770. Mean is equal to 1.4320. Third quartile is 2.8400. Max is 6.9410. Now when you plot xy, you will get the linear model, but this x is a binary. So using the binomial distribution, we have plotted the linear model in the graph. So again, suppose if you want to stimulate from a Poisson model where y is a Poisson. So you want to generate a model where the model is followed by log equal to O0 plus 1x, and the O plus 1x, and O equal to 0 to 5 and 1 equal to 0 to 3. So we need to use the rpice function for this. So set dot seed of 1, so to remember the random normal variates, and x is random normal of 100, and log dot mu equal to 0.5 plus 0.3 star x. So log dot mu is the function where you have 0.5 plus 0.3 star x, and y equal to rpoise of 100 comma exp of log dot mu. And when you get summary of y, so minimum is 0.00, first quartile is 1.00, median is 1.00, again mean is 1.55, your third quartile is 2.00, and maximum is 6.00. So when you plot this, you will get up using the random numbers generated from Poisson distribution, you can create a linear model using this. These are some basic examples I'm trying to give you so that it might be useful to create those. So now we have seen about this distributions, and but what else can this random number generation be useful for? Let's say you would have heard about the common examples where in especially in manufacturing industries, they try to test the products. It is impossible to test products when you are manufacturing lakhs and lakhs of products. So you have to create sample a perfect sample from which the testing needs to be done. So here R allows you to create random sampling methods. The sample function draws randomly from a species set of scalar objects, allowing you to sample from arbitrary distributions. So you have set.seed of 1, and I use sample of 1 to 10 comma 4, which means I need to create a sample of 4 from values 1 to 10. So it gives you a random sample from 1 to 10. Same way again, if I use again, it keeps changing. So, and sample of letters means the alphabetical English alphabets A to Z, and I'm creating a random sample of 5. And for same way, for example, sample of 1 to 10, here I'm trying to just create a permutation out of 1 to 10. So you'll get random, there's just a permutation here. Sample of 1 to 10, again there is one more permutation as given as an example. And sample of 1 to 10, if replace equal to true, so which means you are allowing the replacement. So not necessarily all these 10 will be unique. So for example, here 297 gets repeated again, 97, 8 repeats 3 times, 2 repeats 2 times, 8 repeats 2 3 times, etc, etc. So these are some examples of how to use sampling methods to create particular perfect samples. So to summarize simulation, like these are very much useful when you want to use large sets of data to simulate your model. So, drawing samples from specific probability distributions can be done with R star functions, which are R norm, R poise, R binom, etc, etc. So standard distributions are built in, for example, normal, Poisson, binomial, exponential, gamma, etc, etc. So the sample function can be used to draw random samples from arbitrary vectors. So setting the random number generator seed via set.seed is critical for reproducibility. So if you want to use any random set of Poisson variates or normal variates, you need to use set.seed to remember those values for in terms for next calculations or verifying your previous calculations. So with this we'll finish off simulation, and we'll continue with the rest of the class. Now we'll see about plotting in R programming. So what does plotting basically mean? So the plotting, and plotting is nothing, creating visual effects from your data which will be useful for your clients, which to understand what exactly the analysis or insights are trying to tell you. That is what basically it is. Now we'll see about the plotting. The plotting and graphics engine in R is encapsulated in a few base and recommended packages. So there is the graphics package. It contains plotting functions for the base graphics systems, including plot, hist, box plot, and many others. So lattice is a package which contains code for producing trellis graphics, which are independent of the base graphics system. They include functions like xy plot, bw plot, level plot, etc. So the next thing is grid. Grid, it implements a different graphing system independent of the base system. The lattice package builds on top of grid. We seldom call functions from the grid package directly. So using them is quite a complex thing. So hence the usage. So GR devices, it contains all the code implementing the various graphics devices, including X11, PDF, PostScript, PNG, etc. The process of making a plot. So when making a plot, one must first make a few choices. Now, not necessarily in this order, but you have to make a few choices before deciding on which package to import while you are carrying out with the process of making the plot. So to what device will the plot be sent? So maybe for R programming, the default is Unix is X11. The default in Unix is X11. On Windows, it is Windows OS. On Mac OS X, it is Quartz. So is the plot for viewing temporarily on the screen, or will it eventually end up in a paper? or are you going to take printouts or something like that? Are you using it in a presentation? Plots included in a paper or a presentation, they need to use a file device rather than a screen device. So next thing is like, is there a large amount of data going into the plot, or is it just a few points? Do we need to be able to resize the graphic, etc., etc.? So these kind of decisions you need to take before you have to making the plot from the graphs. Okay. So next kind of decisions is like, what graphic system are you going to use? Whether the base or grid or lattice. You cannot mix these plotting systems. So base graphics are usually constructed piecemeal, with which each aspect of the plot handled separately through a series of function calls. So this is often conceptually simpler and allows plotting to mirror the thought process. So lattice or grid graphics are usually created in a single function call. So all of the graphics parameters have to be specified at once. Specifying everything at once, it allows R um, automatically or to automatically calculate the necessary spacings and font sizes. So base graphics, like what are these base graphics that we use in R programming? Is that, so they are used most commonly and are the very powerful system for creating two-dimensional graphics. So simple graphs like plot of xy or hist of x, it will launch a graphics device if one is not already open, and it will draw the plot on the device. So if the argument to plot or not of some special class, then the default method for plot is called. This function has many arguments, letting you set the title, x-axis label, y-axis label, etc., etc. The base graphic system, they have it has many parameters. So these parameters can set, they can be set and tweaked for your necessary purposes. So these parameters are also documented in questionnaire par. It wouldn't hurt to memorize this help page. So if you want to get the help of the parameters, so use a question mark followed by par. This help page will help you get to know about the base graphic system. So there are what are some of the base important base graphics parameters? The par function, as I told you earlier, it is used to specify uh, global graphics parameters that affects all plots in an R session. These parameters can often be overridden as arguments to specific plotting functions. PCH is the it is a plotting symbol. Default, it creates an open circle. So LTY, the line type. LTY mentions the line type. So default is a solid line. It can be dashed line, or it can be a dotted line, or anything else, etc. So LWD, it specifies the line width. Default is specified as an integer multiple. So, and call is nothing but the color in which the plot is being made. The plotting color it's specified as a number, string, or hex code. The colors function gives you a vector of colors by name. So las las is nothing but the orientation of the axis labels on the plot. So these are the parameters you need to know about when you start working with base graphics. So what are there are some more parameters which can be used in base graphics. BG which means the background color, mar which means the margin size, OMA the outer margin size, default is 0 for all sides, and MF row which means number of plots per row, comma column. Plots are filled row wise, and MF call number of plots per row, comma column. Plots are filled column wise. So these are the important base graphics parameters which you need to know about, which if you want to use the base graphics system. So in those parameters I was telling you about, there are like if you want to see the default parameters, all you have to do is use the par function to get the default values. For example, let's say if I want to get the par of line type, I can go to the R module, I can get par of LTY, and you'll get the resized window solid. So as you can see, the same way if you do for par of line width, you'll get as 1. The default line width is 1, and par of col is black, which means the default color is black, and par of PCH is 1, which the default is a line circle. So some default values, par of BG. BG is background, which is transparent, will be mostly white in color, and par of margin is 5.1, 4.1, 4.1, 2.1, default margins for all the sizes. So par of OMA is 0, 0, 0, 0, and par of M of rho is 1, 1, par of M of col equal to 1, 1. So these are some of the important basic parameters for which you need to know the default values as well when you are constructing plots using the base graphics. So some important base plotting functions. So the first function, and the foremost and the most used function is plot. Plot, it makes a scatter plot or other type of plot depending on the class of the object that is being plotted. So lines, it adds lines to the plot. Given a vector x values and a corresponding vector of y values are a 2-column matrix, this function just connects the dots. And points, same as lines. What points does is it adds points to a plot. And text, it adds text labels to a plot using specified x, y coordinates. And title, it adds annotations to x, y axis labels, title, subtitle, outer margin, etc. Mtext, it adds arbitrary text to the margins, inner or outer of the plot. And axis, it adds axis text / labels. So what are some of the useful graphic devices? The list of devices, it found in devices. There are also devices created by users on CRAN. So PDF, it is useful for line type graphics. Vector format, it resizes really well. It is and it is usually portable. So PostScript is like older format, also vector format, and it resizes well, particularly well, but usually portable. But it can be used to create encapsulated PostScript files. Windows systems often doesn't have a PostScript viewer. Now Xfig. So good of you use use Unix and want to edit a plot by hand. PNG is the bitmap format. It's good for line drawings or images with solid colors. Uses lossless compression, like the old GIF format. Most web browsers can read this format natively. It is good for plotting many points. It does not resize well. So JPG, it is good for photographs or natural scenes. Uses lossy compression. It is good for plotting many points. Does not resize well. Can be read by almost any computer and any web browser. It is not great for line drawings. And again, bitmap, it is needed to create a bitmap files, PNG or JPEG, in certain situations. Uses GoScript. It is also can be used to create a variety of other bitmapped formats that are not mentioned in this slide. So BMP is, again, it is the native Windows bitmap format. So we have like bitmap, PNG, JPEG, and a native bitmap format called BMP. So how do you copy plots? So like there are two basic approaches to plotting. First is to launch a graphics device, make a plot. You can annotate if needed, and then close the graphics device. Or there is one more way in which you can do it. So make a plot on a screen device, it's a default one, and annotate if needed, and you can copy the plot to another device if necessary. It's not an exact process, but I'm mentioning like these are some of the ways in which you can do it. So copying a plot to another device can be useful, because some plots, they require a lot of code, and it can be a pain to type all that in again for a different device. So device.copy, actually it's div.copy. I'll mention it as device.copy here. So device.copy, so it copies a plot from one device to another. So device.copy to PDF, so it copies a plot to a portable document format, that is a PDF file. So I'm using dev.copy, dev.copy.pdf, dev.list. So it shows the list of open graphics devices. And device.next, it switch controls to the next graphics device on the device list. Dev.set, it set controls to a specific graphics device. Next will allocate to the next graphics device. Set will allocate to a specific graphics device. And dev.off is it will close the current graphics device in control. So one simple thing to note here is that copying a plot is not an exact operation, but so why do I say this? You need to create presentations in multiple devices which will be used by the sales team or the marketing team or any other team. So when copying plot from one device to another, you need to know the specifics of how the graph changes according to devices. So now we'll see about lattice functions. So what are lattice functions is that it's an XY plot. This is the main function for creating scatter plots. So BW plot, it's called a box and whiskers plot. You can search in Google. You'll get the better idea of how the data is being formatted into box and whisker plots. Like histograms are your normal bar charts which are useful for creating better representations of data. So strip plot, it like a box plot, but with actual points. So dot plot is nothing, plot dots on violent strings. So splom is nothing but scatter plot matrix. So it likes pairs in a base graphic system, but it's a scatter plot matrix. So level plot, contour plot for plotting image data. So lattice functions, generally take a formula for their first argument, usually of the form y to x f star g. So on the left of the tilde symbol is the y variable, on the right is the x variable. After the are the conditioning variables, they are optional, and the star where it defines the interaction between f and g. So the second argument, it is the data frame or list from which the formula, which the variables in the formula should be obtained. So if no data frame or list is passed, then the parent frame is passed. So if no other arguments are passed, there are defaults that can be used. So hence these lattice functions also play a vital role in creating plots. Lattice behavior. So how do these lattice functions behave? So lattice functions behave differently from base graphics functions in one critical way. So base graphics functions plot data directly to the graphics device. But lattice graphics functions, they return an object of called class called trellis. So the print methods for lattice functions actually do the work of plotting the data on the graphics device. But lattice functions, they return plot objects, that can be, in principle it can be stored, but it's normally, it is usually better, to save the code plus data. That is always going to be useful. But here, instead of code plus data, you'll get plot objects also, which is also recommended. It's not a big issue. And on the command line, trellis objects are auto printed, so that it appears the function is plotting the data. So what are some of the lattice plot panel functions? So lattice functions have a panel function which controls what happens inside each panel of the entire plot. So let's assume, like, we have a x, where random normal distribution of 100, and y uh, is of, it takes x plus random number 100 comma standard deviation of 0.5. So we're basically combining, two random normal variables of 100 comma 100, and you're just adding it. And f is a function of, gl of 2 comma 50. Labels, you're grouping them group 1 and group 2. Now, you're just, forming a xy plot from lattice panel functions. Xy plot of y to x. The condition is f being the factor here. So it plots y versus x conditioned on f. So here, it is normally y conditioned on y to x conditioned on f. So this will be a plot. You can try this in this, and now the our programming is not, in this device it is not supporting plotting, and hence I'm not able to give a example here. But you can always try this, and it will give a pretty good result of the xy plot. So again, the same function, what it basically is, the xy plot of y to x conditioned on f, panel equal to function of x comma y, panel dot xy plot of x. These are the internal functions that gets called when xy plot is declared. So panel dot ab line absolute line h equal to median of y, line type equal to 2. So it basically plots y versus x conditioned on f with horizontal dashed line drawn at the median of y for each panel. So adding a regression line, so xy plot of, y to x conditioned on f, panel equal to function of x comma y, and panel dot xy plot of x comma y, panel dot lm line of x comma y comma col equal to 2, color is equal to 2, and it fits and plots a simple linear regression line to each panel of the plot. So with this, we conclude the, the initial part of the plotting. Even we'll see a lot more on plotting, which will be very useful for constructing, the plots useful for data representation. So in this session, these are predefined slides which I had. So on ggplot2 to be precise. So what is ggplot2? So these are, just, sample modules which will give you, better visualization capabilities. So an implementation of the grammar of graphics by Leland Wilkinson. It is written by Hadley Wickham while he was a graduate student at Iowa State. A third graphic system for R along with Bayesian lattice. So it is available from CRAN via install.packages, and website is, www.ggplot2.org. For, you can get the documentation from that. So what does ggplot2? ggplot2, it basically represents the grammar and abstraction of graphics ideas or objects. So think verb, noun, adjective for graphics. It allows for a theory of graphics on which to build new graphics and graphics objects. Same as, any language, the basic English language, or any language, uh, you get, the verb, noun, adjective, which forms the building blocks of the entire language. The same way here, the grammar is defined for each and every the plot that is going to be decided. So it will create structure for your plot. So it shortens the distance from mind to page. So grammar of graphics as described by Leland Wilkinson. In brief, the grammar tells us that a statistical graphic is a mapping from data to aesthetic attributes, color, shape, size of geometric objects, points, lines, bars. The plot may also contain statistical transformations of the data and is drawn on a specific coordinate system. So this is taken from the ggplot2 book. I'll give you the reference later, which you can use it for further reading purposes. So plotting systems in R, the base system, like what is that base system is, like I explained to you earlier, but it is like the artist, palette model. You know about a palette artist uses to draw his paintings. So it starts with a blank canvas and it builds up from there. It start with plot function or similar. So you can use annotation functions to add or modify text, lines, points, axes, etc. Now uh, the base system is, it is convenient. It mirrors how we think of building plots and analyzing data. So it can't go back once the plot has started. That is to adjust margins, need to plan in advance. So it is difficult to translate to others once a new plot has been created. There is no, the graphical language is missing in the base package. So the plot is just a series of R commands, which is useful for it. So moving on, the lattice system that we saw, the plots are created with a single function called like xy plot, bw plot, which is the box and whiskers plot, etc. So the most useful for conditioning types of plots. So looking at how y changes with x across levels of z, things like margins slash spacing is set automatically because the entire plot is specified at once. So it is good for putting many plots on the screen. So but there are some disadvantages as well. Sometimes it is awkward not to specify uh, an entire plot in a single function call, like so the annotation and the plot, it is intuitive. The use of panel functions and subscripts difficult to wield and requires intense preparation. You cannot add to the plot once it is created. So those are the disadvantages with the lattice plots. So plotting systems in R, ggplot. What is this ggplot2? It splits the difference between base and lattice. Automatically deals with spacings, text, titles. But it also allows you to annotate by adding. It has superficial similarity to lattice, but generally easier or more intuitive to use. So default, mode makes many choices for you, but you can also customize. The basics, qplot. What's or it works much like the plot function in base graphics system. It looks for data in a data frame, similar to lattice or in the parent environment. So plots are made up of aesthetics, size, the aesthetics as in the which describes the physical the variables of a plot, the size of it, the shape, color, and geoms are like the geometric attributes, points and lines. So the basics, the q plot and gg plot too. So factors are important for indicating subsets of the data. That is, like if they are to be have different properties, they should be labeled. The q plot hides what goes on underneath, which is okay for most operations. And ggplot is the core function, and it is very flexible for doing things qplot cannot do. So example data set, this data set is available from online. You can take it from any kind of online resources, but this data set I have taken it from free resources. So I have imported this, the library of ggplot2. ggplot2 package has to be brought into reference using the library command. And when you check, there is a data frame called mpg, and when you see the structure of it, I'll explain you the structure. There is five to 10 columns in a manufacturer, model, display, air, so cylinder, transaction like drv, city, highway, fl, class, etc, etc. So now we can see manufacturer is a factor with 18 levels, model is factor with 38 levels, display the year is integers, cycle is integer, trans is factor, etc, etc. So still you have, like, there are like lot of things in this data set. So if I want to use a simple ggplot, ggplot hello world. Hello world is a basic, for any programming language, but here I'm just saying hello world using the mpg function. So this is how I use the qplot to plot the thing. So here qplot of display as the x coordinate, hwy as the y coordinate, and the data file is nothing but the mpg file that I'm being important here. This is as simple as that. So this marks the display and highway data, and it gives you a pretty good result. So modifying aesthetics, how to modify the aesthetics. So in the this is a blank graph. So if I want to color code the data inside it, so how do I do it? So you can use the color aesthetic when I specify, for the drv variables as by the drv as a factor, and I want to color using the drv factor. If I mention it, so it will mention for 4 f and r and different colors. So display highway data equal to mpg, and I am adding a parameter for color which will include drv for those factor, and it is modifying the aesthetic. So adding a geom. So now I want to add a line which marks. So I want to mark a line, point line. I mean, it's basically work with points, but I want to mark it as a smooth line. So qplot of display highway comma data to mpg geom equal to cf point and smooth. So it draws a smooth line from the in the data from the center to the center. So now if I want the points to be converted into using the factor drv to create a histogram, so how do I do it? So qplot of hwy comma data equal to mpg comma fill equal to drv. So this is how I convert the data into a histogram. Basically you saw a smooth line. Now if I use fill equal to drv, the data gets filled in and it forms a basic histogram. Now facets, what are facets? Like facets are simply splitting up the data part. So now if I want to split by the variable facet drv, like I want to show for 4 f and r using separate charts. In the single chart it gets split into 4 f and r. How do I split that? So same way, the simple adding a parameter into it, qplot of display highway comma data equal to mpg, just add facets equal to dot drv. Now when you add dot drv into it, the data gets split into 4 f and r. So this is how you can same way you can split like highway count facets drv bin width equal to 2. Now this will create histogram for 4 f and r. You can create multiple facets based on your data, which will be really helpful for your analysis. So here I have a data set called MMA-CS cohort. So this study I took it from the online resources. So it's a mouse allergen and asthma cohort study. So it was tested between Baltimore children aged 5 to 17, persistent asthma and exacerbation in past year. Studies indoor environment and its relationship with asthma morbidity. You can see the publication in this URL. So this data, it has exhaled nitric acid, fine particular matter PM25, and sensitized to mouse allergen. So these are just random data. Forget about the data. Just need to know about what are the functionalities of those, and then it's a data frame where we have like 750 observations with 5 variables. I'm not going to give the data. You can download it online. And now if I want to create a histogram of exhaled nitric oxide, so I just need to create a log ENO count and just a data matrix. Just it will give me the basic histogram. Moving on, if you want to create a histogram by group, now this is where you bring in the factor fill equal to mopos. So mopos is a again variable in that. By that variable, whether it is yes or no, it will create the subset inside the histogram. So this is how I create. Moving on, so If I want to create smooth density curves, like if I want to create a density curve, how do I do that? So no, I've shown you about the geometric function point smooth lines, and I know in this way, same way you can create density functions also. Same way, use qplot log of comma data equal to MMACS, comma geom equal to density. When you use this, you will get the density function. Qplot of log of comma data equal to MACS, geom equal to density, color equal to mopos. I am splitting the density function into by the factor mopos, yes and no. So this will give you the simple density smooth curve. Like so, I'm trying to create certain scatter plots here, which will give you better ideology about qplot and other stuff. How does it work, etc. So now this is a simple qplot between log of the particulate matter between log of exhaled nitric oxide. So and data equal to this is the simplest graph. And here I want to change this circle to triangle, smaller triangles. How do I do that? So here I create smaller triangles for S and circles for no. Just these are not, we are not exactly defining a triangle, but just by using shape equal to mopos, the graph gets differentiated by the factor mopos. Same way again, if you want to differentiate by color, use color equal to mopos. This will be differentiated by a color in this graph. So combining all the graphs that we saw earlier, how can we create a graph which is very much intuitive, and which helps you which helps you understand how the data works in particular. So it's a q plot of log of PM25, log of comma data equal to MACS, color equal to mopos, geom equal to C of point, comma smooth, method equal to LM. So moving on, to get into the next thing. So now if I bring about to create facets also in this data, I create a q plot of log of PM25, log of data equal to MACS, same as geom C point comma smooth. I create a smooth line, and method equal to logical modeling, and I create facets equal to mopos. So when I create facets, it creates one for no and one for S. So we have come to the end of qplot. So what is the summary of qplot? The qplot function is the analog to plot, but with many built-in features. So hence it is much more useful. We have facets, we have the points by differentiation by color, differentiation by shape, and you can use geometry functions to draw point lines, splines, and you can create density functions, those kind of things. Qplot brings in a lot of thinking into your stuff, and it gives you a wide variety of graphs that can be constructed. So if you see the syntax also, it is in between base and lattice, much not complex when you consider this. And it produces very nice graphics, essentially publication ready. If you like the design, you can publish online and you'll get better results for your products. And it is difficult to go against the grain or customize. Don't bother. Use full ggplot to power in that case. So these are the resources that I have verified. So you can use this for creating better q plots. The ggplot2 book written by Hadley Wickham, our graphics cookbook by Winston Chang, examples base plots and ggplot2. ggplot2 website, these are open source materials. It is always welcome to use these. ggplot2.org, ggplot2 mailing list, go.gl odw3ub. It is primarily for developers. So with this, we'll conclude this plotting of plotting using qplot, and we'll see furthermore in the plotting in the next sessions. So we will see about ggplot2 in detail, and what it can provide you with in terms of the graphics part. So what is actually ggplot2? As you have seen earlier, it is an implementation of the grammar of graphics by Leland Wilkinson, And the grammar of graphics, it represents an abstraction of graphics ideas or objects. So it not necessarily it directly has a meaning as to the English or any language grammar. Grammar actually forms the backbone of any language. And here, when you understand the backbone of what graphics can be, so like you have verb, noun, adjective in any language. Now, think in terms of verb, noun, adjective for graphics, and that allows you to give a proper structure to your, the graphics properties in R programming. It allows for a theory of graphics on which to build a new graphics and graphics objects. Moving on, what are the basic components of a ggplot2 plot? So you need to have a data frame. A data frame is nothing but table data extracted into it. And aesthetic mappings on the look and feel, how data are mapped to color size, length, everything. So geoms are like geometric objects which are like points, lines, shapes, etc. Facets, these are used only for conditional plots. I'll tell you on the way. Stats, statistical transformations like binning, quantiles, and smoothing. So if you are into more into statistical uh, statistical computing, you will know about binning, quantiles, and smoothing. And if not, there is not an issue, but we can proceed with the previous one. Next one. Scales. What scale an aesthetic map uses? Example, male equal to red, female equal to blue. So scale is nothing but a legend that you see on any kind of map. And the coordinate system, the XY axis coordinate system. So how to build plots with ggplot2? So when building plots, rather than using qplot, uh, the artist palette model may be the closest analogy. I'll tell you later. Earlier we saw about qplot. Here I'll show you about artist palette. So these plots are built up in layers. You can plot the data, overlay a summary, metadata and annotation can be given. Metadata is nothing but the data about how the data about data. So an annotation, how do you mark? So this is some online resource I took from data BMI. So uh, there is a PM 2.5 is a disease, and asthma is again a disease you know about. So BMI, body mass index, modify the relationship between this and this. So you don't have to know about the data here. So you just need to know how it is being constructed. So there is a data for normal weight. When we are using uh, nocturnal symptoms mapping with normal weight. Nocturnal symptoms is a data where you get whether the person was able to sleep or not, how many hours he is being able to sleep. So those kind of things. So qplot, when you run this, facets is equal to BMI cat, geom equal to C of point comma smooth. We are running a point and a smooth points, and method is equal to logarithmic model. So this is the basic plot that you get. So I'm trying just map normal weight with nocturnal symptoms and overweight. Mm. So as you can see, the nocturnal symptoms are more for the overweight category, which is indicated from the data. So this is how we constructed the basic plot for um, using ggplot. So building up in layers. So this is the data frame, the BMI category, weight, overweight, and the log of PM25 and nocturnal symptoms. So this is how the graph was conducted. Aesthetics is the look and feel. Q equal to ggplot of the data frame, comma AES of log PM25, comma nocturnal symptoms. So the summary of G gives log of PM25, BMI cat, nocturnal symptoms mapping. X-axis was log of to PM25, Y is nocturnal symptom faceting. Faceting is facet null. So this is a summary of the ggplot object. So Q equal to G equal to ggplot of the same is being printed here. So when you print G, no layers in plot. So you have to explicitly save and print the ggplot object. Otherwise, it will not work. We cannot just print of G and get the ggplot. So what you can do is you can save p equal to g plus geom point. Geom point is the function for calling the geometric points. So now when you print of p, and or also you can auto print plot object without saving using this g plus geom point of the function geom point. Now you'll get first plot with the point layer. So now you see the nocturnal symptoms mapped with the data, log of PM25 x-axis and nocturnal symptoms y-axis. So adding more layers, making the data more smooth. So in geometry of smooth, if you use the method logarithmic model, as you can see, the data is much more smoother and can compared to without smoothing. Adding more layers of facets, labels from facet is also available. So when you can add facets will give you multiple the nocturnal symptom log of PM25 was x-axis, nocturnal symptom was y-axis, and you can add facets of BMI category, normal weight and overweight. So now you'll get for both. So that's how you differentiate using the facets. So we are looking at the annotation part for the plotting of ggplot. So what are the labels used? X lab, Y lab, labs, GG title. Each of the geometric functions, as you can have the options to modify, as we saw earlier, where the smoothing was using done using the model LM. So for things that only make sense globally, use a theme. Example, legend position, theme of legend dot position equal to none. This will be, a lot of people will not be able to understand, but it is like simple. The position of the legend is kept as none. So two standard appearance themes are included. The default theme is the gray background, and a theme black and white. It will be like much more plainer, like the screen that you're seeing right now. So how to modify the aesthetics, I mean the color, size, everything. So you had a plot g plus geometric point, you had the points, and in that points you have multiple parameters you can pass it inside. For example, you pass the model that being used as LM earlier. Here you can mention the colors that can be used for modifying the aesthetics. So color is equal to steel blue here, and color equal to BMI cat. BMI cat, when you give the category as color, it will assume, let's say in the BMI category we saw normal weight and overweight. So in the normal weight and overweight categories, it segregates automatically with two different colors, and size equal to 4, and alpha is related to the image coding that you can ignore as of now. So next thing, moving on, how to modify the labels in a Gplot. So nocturnal symptoms versus log of PM 2.5. So the name labs function for modifying the titles and XY axis labels. So here, this nocturnal symptoms is the label used. Earlier, if you have seen, it was very much from the data directly extracted here. But if you see here, you're modifying the title used here. Log G plus geom point is color BMI cat, color differentiated with BMI category, plus labs of title MMACS cohort, which is the title of the slide, that is, and plus labs of x equal to expression, the x-axis being modified as log star PM 2.5, and y equal to nocturnal symptoms. So that's the reason you are able to get the titles assigned properly to those labels. Moving on. So how to customize the smoothness of the line or points that we are drawing here. So here, so we are again in the same function. We see g plus geom point, aesthetics color BMI cat, size equal to 2. The size has been reduced. The size of the circles has been reduced to 2, and alpha equal to 1 by 2. You can ignore that now. Plus, now for the point you saw, and next for the smoothing, you can see geom smooth. You are mentioning the you are increasing the size equal to 4, and line type equal to 3, which means dotted squares, and method equal to LM. So this logical model being used to create the line here. Moving on, how to change the theme of the plot that we are working on. So now you can see again the same function. So using aesthetic color BMA code, again normal weight and overweight segregated, plus theme underscore black and white, base family equal to time. So you can see it is much more plain than the previous backgrounds that we have seen. So if you're able to travel back in the video, you can just move back and see the screen there, and it's much more different when you use theme black and white, base family equal to times. So moving on, so you should know about the access limits and about those. So in that test data, uh, there is again, do not go into the data sets right now. These are just examples to show you how ggplot can be used. So test data, the data date frame, there is a 100 row data frame, and in that uh, the outlier is marked. So the 50 comma 2 is less than this is the 100. So this is the outlier. So when you plot this, what you get is q equal to ggplot test dat. So aesthetics x equal to x and y equal to y. So as you can see, the outlier has been marked clearly in the next graph that is shown here. This is the outlier that is shown. So you should know about always an access limit. So so when you have access to the access of 0 to -3 to 1 to 3, and when you have um, the test data, in the test data the value for 50 is 100, so this is an outlier and just goes beyond. So I always recommend to remove outliers or replace it with the average of the remaining data, so that the outlier comes down to this level. So now, so you're limiting. In the previous one we saw the limit being exceeding here. So how to so when you include the outlier, the data seems coordinate Cartesian outlier is included here and it's not shown in the graph. But here the limit, in this limit, the outlier is not included. You can see the data point for 50 is missing here. So when you limit -3 to 3, your outlier will go missing. So outlier you can include using coordinates of Cartesian product, like Cartesian y limit of c of -3 comma 3. So uh, how does the relationship between the data frames, the PM25 2.5 as a disease, and the vary by BMI and the consumption of nitrous oxide is in the data? So here I think you can ignore this for this now. We don't have the data with us now. But this slide was solely meant for analyzing the QQ plots. So so this is the final plot that was arrived in that data. So you can get the data precisely here. This is the non-default plot. This was assigned using that aesthetics labs function, and transparent points you can make alpha, just alpha and aesthetics, and multiple panels can be added, and smoother lines and labels title. These are all shown in the same graph. That's the thing. So multiple facets are added to create these multiple panels for smoothing, and labels, title, everything is set properly. Now this graph makes much more sense than anything else. So the code for final plot was, including this facet trap, BMA cat is no, to composition, forget about that now. So smoothing method LM was used, color was steel blue, and theme black and white base family Avenir. There are like a lot of base families, you can Google it. And labs of X equal to expression, log PM25, Y equal to nocturnal symptoms, title MA6. So all these code, when you run, you'll get a plot like this, which will help you in much more easier ways. So now moving on to the summary. So ggplot2 is always it's very powerful, and it is flexible if you learn the grammar and the various elements that can be the aesthetics, the smoothing part, the points part, everything. So if you try to understand that, ggplot2 is almost like it's very powerful. And there are many more type of plots can be made, explore and mess around with the package. So the plot, as we have mentioned in the previous part one, so it will be the references are mentioned. We'll see about plotting and color even more in the next slide. So why do we emphasize more on the plotting part is that uh, the analysis part is as important as the plotting part. Plotting will give you the better visualization of data, which will make you understand the data even more. So when you know the plotting or the graphics or visualization part is almost as equivalent to the analysis part when you uh, ca- when you are when you want the product to be insightful. So now the default color schemes for most plots in R are like horrendous. Like the default schemes that R programming initially provided was not so good. So uh, uh, so I don't have a good taste, but like even I know that. So recently there have been developments to improve the handling and specification of colors in plots, graphs, etc. These are developed by numerous programmers who are supporting to the R programming community. So there are functions in R and in external packages that are very handy. We'll see about that in this session. So colors 1, 2, and 3. What do they indicate? Colors 1 is blank black, so plain white, and color 2 is red, and color 3 is green. So using the parameter call equal to 1, call indicates color. So you can generate data with random colors. So default uh, image plots in R. So when you take a graph, so when you take a XY axis and you want to create a heat map, so where exactly the densest point is plotted can be analyzed using a heat map. So basically, when you see this image, you'll get that most of the data is concentrated around this region, and this region being the lightest. This region is also the lighter regions, and this region is also lighter, but the denser regions you can see around. So this is a heat map and this is a topography map. So it will clearly like give you the contours of the data available. So in which will able to differentiate the other set of data from the remaining. So moving on, how to use the color utilities. Now, as I told you earlier, there is a package called GR devices, and this package will be used for the color utilities. So they have basically two functions. One is called the color ramp, and the other thing is called a color ramp palette. So these functions take palettes of colors and they help to interpolate between the colors. So the function colors is list the name of colors you can use in any plotting function. So you can test it whenever when you download this GR devices package. Right now I don't have this package, so I'll explain you in basics of whatever I created, whatever the slides I created. So the color ramp palette. What is that color ramp palette? It takes a palette of colors and it returns a function which takes value between 0 and 1. So it indicates the extremes of the color function. For example, if you take select the color as gray, between 0 to 1, the 0 will be the lightest and 1 will be the darkest. So it will indicate the extremes of the color palette for a particular function. Now, what is color ramp palette? So uh, it takes a palette of colors and it returns a function that takes integer arguments. So the basic difference is the integer arguments, and it returns a vector of colors interpolating the palette. So what happened in the earlier graph was this was heat dot colors. This comes from the color ramp palette. So it takes the input and it returns integer plots, integers for each of the integer vectors which interpolates the palette. And this heat dot colors heat map or topographical map was created using the color ramp palette. So as you know, every color is constituted by red, blue, and green. It was mentioned as RGB. So now when you see a palette of 0, as you can see, the red is marked as 255 and green is 0, blue is 0. So when you are seeing pal of 0, when you see pal of 1, you'll get 00255, which means blue is 255 and green is 0 and red is 0. So pal of 0.5, when you want to divide, so it is actually indicating the extremes of the color ramp. So here, when you mix colors red and blue into the color ramp, so the extreme is 0 to 1. When it is 0, it will be extremely red, and when it is 1, it will be blue. And when it is in the midpoint palette of 0.5, it will give you red is 127.5 and blue is also 127.5, equally divided colors at the midpoint exactly. So as I told you earlier, 0 to 1 describes the extremes of the colors. So you can use the same function. You can create a sequence of 0 comma 1, length 10. So it ranges from 255 to 0 and 0 to 255, and always green will remain 0 because the function was created only for red and blue. Now we'll see about the color ramp palette. So we earlier saw about color ramp, now we are seeing about color ramp palette. So now it will return it returns a vector of integers. Like if you see the color ramp palette of CF red comma yellow, so when you return pal of 2, it returns numerous values. These values will be interpolated to the heat maps or graphs. So moving on, wanted to discuss about a package called R Color Brewer. So one package on CRAN which contains interesting or useful color palettes is this R Color Brewer. So here it is different from the GR devices package. So we have three types of palettes in R Color Brewer. So we have a sequential package, diverging, and qualitative palette. So palette information can be used in conjunction with color ramp and color ramp palette. So the same way, I'll discuss more on this in this coming slide. So these are the palettes that is available. So as you can see, this is purple, red, purples, red, purple, reds. You can see this graph in detail. So you can see spectral, pastel, pad, accent. So there can have a lot of color palettes available. This will help you in creating better colorful plots. So our color brewer and color ramp palette, how do they work together? So when you import the library R color brewer, so like this is the function used to import R color brewer package, and I'm creating colors brewer dot pal of 3 comma bugn. So I'll just even I'm not sure about the colors. I think it means blue and green. So when you have pal of color and palette of calls, so image of volcano comma call of pal 20. So you will see the same graph using blue and green. So shaded accordingly. So this color blue dot blue green, this is the exact colors. So when the data is mapped to the color ramp palette function, So in that volcano image, you can see that the data being used colorfully. So this is not the best visualization, and you can come up with better things when you are able to use the R color brewer package carefully. So there is a function called the scatter function. So this function will give you the, again, as always, the concentrated data versus the not so concentrated scattered data. So you have a function with let's say we are creating a random normal random 10,000 random integers with rnorm function, and we are creating 10,000 again variables with rnorm function in y. So when I create the smooth scatter of x comma y, so you have a range between -4 to 4 for y, and range of -0 to 4 in this. So when I create this, you'll get where the random integers were generated most was this area, and where the random integers were scattered, like less sparsely populated, are around this area. So this smooth scatter function will be useful when you want to map density of functions. Like, so some other plotting notes: the RGB function, it can be used to produce any color via red, green, blue proportions. As you always know, um, the RGB function, RGB forms the basis of any color that can be formed in and around the world. Any color in the world can be formed using the RGB uh, proportions. So color transparency can be added via the alpha parameter. So alpha parameter that we saw earlier examples. So the alpha parameter describes the transparency of a image. The color space package can be used for a different control over colors. So this is a scatter plot with no transparency. So now you can see the area more densely populated. As you can see, a normal distribution will have the densely populated values to be around the mean. So as you can see, for the mean here it is 0. So that's the reason you're finding a lot of variables. As you can see, if you plot it using a different graph or a line graph, you'll get a perfectly shaped bell curve along the data. So the transparency is null here, as you can see in the data. So which means the darker spots, this area indicates the densely populated region, and this is the sparsely populated region. Now if I add transparency to the scatter plot, so now as you can see, plot of x comma y color equal to RGB 000 comma point 2 signifies the alpha value, which will indicate the color transparency. Now coming on to the summary of this one. So careful use of colors in plots, maps, etc. They can make it easier for the reader to get what you're trying to say. So, like I said, in the industry, the analysis of data is very important. But when you're not able to explain the data properly, the analysis, the insights properly to a customer, so it will make things difficult on the client. So that's the reason I'm saying again and again that the end product, the color plotting, is much important to us as the same way as the analysis part. So the R color brewer package, it is an R package that provides color palettes for sequential, categorical, and diverging data. And the color ramp and color ramp palette functions, they can be used in conjunction with color palettes to connect data to colors. And transparency can sometimes used to clarify the plots with many points using that alpha function. So this is the summary of plotting with colors. Now in our programming, we are going to see about the usage of date and time, and how effectively you can use those variable types for better usage of the data. So uh, dates and times in R, they have special representation in R programming for dates and times. So there is a class called date which represents the dates for, and there is a times are represented by the POSIX CT or the POSIX IT class. So I'll tell you exactly what are those. So Any programming language, actually dates are stored internally as a number of days since 1970 1st January. So again, times are also stored as internally as the number of seconds since 1970 1st January. So for example, if you have uh, the days as like 1971 January 1st, it will be exactly the number of the it will be stored as 376 or 75 based on the number of days since 1970 into the data. Same way for times, but it is the number of seconds since the first of January 1970. So this happens with most of the programming languages, so there is nothing much different here. So dates are represented by the date class and can be coerced from a character string using the as.date function. So I'll start using our programming tool to explain this how it happened. Now moving on in this function, I'll show you how to use as.date of the function. It's 1970 0101. Now, when you print X, you'll get 1970 0101. I told you earlier, a date function is a date is stored as the number of days since 1970 101. But here, I have taken this date and I'm storing it as date itself. So I'm coercing the date from a number to the date function itself into variable X. Now if this class has been defined as date, so now if I want to change the class, I use the function unclass of X. So now the coercion is removed and it is marked as 0. The reason it is marked as 0, it is only one date. So it is one day, it is the first day, so the number of days since 1971 1 is 0. Now if I want to if I change this date as 2, and again I perform the unclass of X, you will get 1. It is only one day since 1970 101, and hence I'm getting the result as 1. So the same way POSIX CT or POSIX LT class, so times are represented using the POSIX CT or POSIX LT class. So now POSIX CT is like, it is a very large integer under the hood. It is a useful class when you want to store times in something like a data frame. Or POSIX LT is like a list, so it's all depends on how you are trying to save. So it's a list underneath, and it stores a bunch of other useful information like the day of the week, day of the year, month, day of the month. So POSIX CT, it stores all times in a data frame. POSIX LT on the other hand, it saves other useful information also into the data. So there are a number of generic functions that work on dates and times. Weekdays, for example. So weekdays gives the day of the week, and months gives the month name. Quarters give the quarter number. For example, Jan to March is quarter 1, April to June is quarter 2, the same way till October to December. Now let's see some examples for using times in R. So times can be coerced from a character string. Use the as.posixlt or as.posixct function. So let's say uh, there is a function called system time. It will give the local system time into the variable. Let's assume we are moving into we are putting that system time into the variable. So let's say we have a variable called x where we have sys.time. Now when I print x, you will get that from the date time here, this is 2015-09 for 5th 9th of May 11:36 11:37 p.m. So now, so if I use this function p as dot posix of posixlt of x, Now still the same as stored is. So now if I want to unclass names of unclass of P, you will get it contains second, minute, hour, month, day, month, year, weekday, year, day, DST, zone, and the GMT is off. So these are the names available in the POSIX-LT function. Now, so if I want to see only the second variable, how do I select that? Using the dollar function. We have seen earlier, using the dollar function, you can extract only individually. So as you can see, it is 36 and this is all milliseconds. 36.24335 is a value that is stored for seconds. So if you want to extract, so p dollar, in the same way, if I use mday, okay, this is, I'll tell you the example later. So same way you can do for minute. Okay, that was used. So mday gives the day of the month. So as you can see, 9th of May. So if I want to get hour day, what I can do? 128 from beginning of 2015, from uh, January 1st. This day, May 9th, is 128th day of the year. So this is how you can use the times function in our programming. So we can use the POSIX CT format also. Same way we can store POSIX CT also. So we will have, let's say, the system.time is already in POSIX CT format. Now if I print X, you will get same day. And if I want to see, so this data, this system.time is already in POSIX CT format. So now if I use unclass of X, what happens? You get a value with which is a 10-digit number, and this 10-digit number is nothing but the number of seconds since 1970 1st January and the start of the first second. This is the number of seconds since. This is how the data is stored inside the time class. So now if I want to, let's say I use the same p dollar second. I have a class X, so I need to use X. So as you can see, this operator is invalid for atomic vectors because this doesn't have the names. So if I want to do that, so I can, what I can do is can use as dot POSIX LT of X. Now you'll have P. Now if I use P dollar second, now I'll get 3 seconds followed by the number of milliseconds. Now moving on, so there is a function called strp time, which will be very much useful when you have the date written in multiple formats. Like there is some people write the date as year, dd, month format, format, or we can use dd, yy, DDMMYY format or MMDDYY format. So it all depends on the region they're in, and like there are multiple usages for writing the date and time. Now, so we have a date string here which has January 10th, 2012, 10:40, and December 9, 2011 x equal to, now if I use x equal to strip time of date string, percentage %b, percentage %d, percentage %y, percentage %r, percentage %m, I'm trying to convert the data into this format. So this will convert the January 10th, 2012 1040 into 2012 110 for 104000. I'm just converting the data into like the same format, percentage %d, y, percentage %r, percentage %m. So again, this was December 9, 2012, 2011 also converts to 2011, 12, 09, 09, 10. So now the class of x is, it will give POSIX LT. So the default strp time function will move into POSIX LT or POSIX x, POSIX t. So always for remembering the formatting strings, check question mark step strp time for details. Now, what operations can we do on dates and times? So the simple mathematical operations on dates and times can always be used. Well, to be honest, you can use plus and minus, the plus and minus operators. You can do comparisons also. That is when you can compare whether the date is equal to, or date is less than, or date is greater than, those kind of functions. So now, if I want to get a subtraction of two dates, how I can do this? So let's say we have a date x which has as dot date of 2012-0101. Now I have a date which is in strp time. So like y strp time of 9 Jan 2011 11:34:21. Now if I use percentage %d space percentage %b percentage %y percentage %h colon, this is the format in which you want to print the data. So the percentage %s is your second. Now this is done. Now we have x and y. Can print x, this is y is not applicable. So now if I want to do x minus y, so non-numeric argument to incompatible methods. So what we can do is we can convert x to POSIX LT function. As you see, strp time is the default stored as POSIX LT function, but this is stored as a date class itself. So now if I want to I can convert this to as dot POSIX LT of x. I'm assigning x to x itself. So now we have x and y in the same format. Now if I use x minus y, time difference of n seconds. So now here it is incompatible data format. That's the reason we are getting the result. Otherwise you'll be getting the time difference of 356.3 days. And so the problem, as you can use as.POSIX LT of x, we can also use functions, we can use unclass of x to get the exact value also. So moving on, so Even you can keep track of leap years, leap seconds, daylight savings, and time zones. Daylight savings is a concept in United States and a lot of other countries as well. But time zones, we are currently in the IST, Indian Standard Time. So now let's see some functions. So let's say we have a date 2012 301 and 2012 0208. The reason I'm taking 2012 is that it's a leap year. Now if I use x minus y, time difference of 2 days, and how exactly I got that is that we have 2012 March 1st and 2012 Feb 28th. Now moving on, if I'm using a function called x where you have 25 and 2012 with one stored as in, so of 2012 10 25 01 00 00. Same way I'm creating a function for y which is 06 comma tz equal to gmt. Now we can see, so 2012 25th of 2012 October and the time is 1. It is stored in IMT, and 2012 10:25 and the time is stored in GMT. Now if I do x minus y, normally if both are in same time formats, if I should get minus 5 hours. So now I'm getting minus 10.5 hours. Why is that? The reason being the time difference between GMT and IST is 5.5 hours. So now GMT 2012 10:25 06 is actually 2012 10 25 plus 06 GMT plus 5:30. So it will be 11:30 in IST. So that's the reason you're getting x minus y is minus 10.5 hours. If you do minus y minus x, you'll get in 10.5 hours. So that's the reason, like GMT plus 5:30 is IST. That's the reason you are getting the time difference as 10.5 hours. So this example is indicated for EST. So that's the reason you are getting 1 hour. Now to see the summary of dates and times. So like as I said earlier, dates and times have special classes in R that allow for numerical and statistical calculations. Dates use the date class, times use the POSIX-CT and POSIX-LT class, and character strings also can be equals to date or time classes using the strp time function or the as.date or as.POSIX-LT or as.POSIX-CT functions. So with this we conclude the date and time. Now we will see about regular expressions in our programming. What are Regular expressions. So if you know anything related to text analysis, regular expressions will constitute most of the uh, premises of text analytics. So they are understanding these will be very much useful in analyzing unstructured data. So regular expressions can be thought of as a combination of literals and meta characters. What are these? I'll show you with examples in these slides. So to draw an analogy with natural language, think of literal text forming the words of this language and the meta characters defining its grammar. So the meta characters, again, it's related to the metadata and database management, where meta characters define will tell you what those characters are really for and what this character's meaning really is. So regular expressions, they have a very rich set of meta characters. So moving on, what are literals? So I'm showing the simplest pattern. Only literals. Literals are nothing but uh, just a word or characters just matter directly. I have a set of examples here. So as you can see, there are like multiple text which have the word nuclear in it, but the usage of nuclear is different, and the sentiment behind every usage is different. For example, the first line, ooh, I just learned that to keep myself alive after a nuclear blast, all I have to do is milk some rats, then drink the milk. Awesome. So this is think of it as like some kind of a Facebook or a Twitter feed that's coming out. So like in the first sentence, you saw someone like making fun of the nuclear blast. So you have the word nuclear along with it. So Lavoisier says nuclear weapons are mass macho. So Laozi is some kind of Mexican statement where you have the nuclear weapons are, it defines the characteristics of a male. So chaos in a country that has nuclear weapons, not good. So this is one more sentence. My nephew is trying to teach me nuclear physics, or possibly just trying to show me how smart he is. So I'll be proud of him. So lot lol, if you ever say nuclear, people immediately think death by radiation. Lol. So you see multiple usages of the word nuclear here. So let's say there is a text analytics you have to run, and you want to see how many people how people are talking about a nuclear test or a nuclear blast that happened. There cannot be a nuclear blast, but if there is any kind of nuclear test run by any countries, and is there someone who is talking on Twitter or Facebook. So as you can see, the word nuclear is spoken by a lot of people, and as you can see from the text, there are the sentiments are much different. So in these, your task will be to identify those which talk relatively to the nuclear test or something like that. So the problem definition may vary, but here if I use slash nuclear, it will given using R programming, the slash nuclear will match to all these statements, and from these statements you can extract the statements that you require from the for your analysis purpose. So it is a simple literal, which means nothing but you are searching for the text nuclear, that's all. You are searching for nuclear, and if it is found in that, it will return a positive match. So again, I extracted these examples from online. So as you can see, the next literal Obama so would match to the following lines. So for example, there is you can see as these will be like Facebook or Twitter feeds. Politics are dumb. Not too long ago, Clinton was saying Obama was crap. Now she's vote for him and unite. WTF, screw on both, plus McCain, go Ron Paul. So this is some kind of a Facebook or Twitter feed wherein a user is showing his anger towards Obama. So now Clinton concedes to Obama, but will follows listen. So Clinton, as they are talking about Hillary Clinton, so that's the reason we are getting will her follows listen. Are we sure Chelsea didn't vote for Obama? Thinking Michelle Obama is terrific. Jet lag, no sleep, early morning to Starbucks. Miss Obama was moving. So Again, here also you found a lot of statements relating to Obama. So if there is an analysis where you want to find how the people who are talking about Obama and their sentiments, you need to perform a sentiment analysis. So you can move on to use the simple literal Obama will give you all these sentences where the word Obama was used. Now, so the simplest pattern that I showed you for nuclear and Obama are best examples, which contains only of literals. A match occurs if the sequence of literals occurs anywhere in the text being tested. What if we only want the word Obama or sentences that in the word Clinton, sentences that end in the word Clinton? So I'm being specific here where I want the sentence that ends with Clinton. The last word is Clinton or Clinto with a capital C, with a small c, and n being removed in the end. So if I want to extract the word that in the end of the word, how should I do it? So now regular expressions, using regular expressions uh, with addition to that simplest simple literals, you can get to those kind of things. So uh, what are the possibilities that you might need later? So we need a way to express white space word boundaries, sets of literals that might be you need to extract from the data, the beginning and end of a line, and alternatives. Like if there is like you want to search for a same word can be described like someone can use a nickname for a person. For example, the previous example we saw Clinton, so maybe his nickname was Clinto or something. But you want to see or Clinton or Clinto, you want to search both. So how do we do that? So we have these meta characters which will define the set of literals, and they will be helpful for extracting those kind of data. Now, moving on, what are these meta characters that helps you identify the letters? So there are some meta characters which represent the start of a line. So if I use uh, exponential symbol followed by any sentence like I think, so you are trying to find sentences where you have the sentence begins with I think. So, for example, you have let's say, so consider the possibility of analysis when you're doing this. So, let's say we have a Twitter feed of let's say some 1,500 users for the past 1 year, and you want to search specifically in that feed. You will get like most of the time in any kind of any kind of companies, you will get the data in a simple text file where you have the feed Twitter feed from the username and the timestamp and the Twitter feed. So you're just going to do a some small analysis on the data that we are getting. So let's say I want to extract only the data with the starts with I think. So I need to use a expression which will start with exponential I think. So this will match the line. So I think we all rule for participating. I think I have been outed. I think this will be quite fun actually. I think I need to go to work. I think I first saw Zomo in 99. So these all sentences will be given as a result when you're searching for exponential symbol followed by I think. Now, so we saw exponential character being explaining the start of the sentence. Now there is a symbol called dollar which will represent the end of the line. For example, if I want to get every sentence that ends with morning, so what should I do? Like, so use the meta character dollar along with morning. So the literal is morning and followed by the meta character dollar will match the following lines. So for example, well, they had something in this morning, then had to catch a tram home in the morning, dog obedient school in the morning, and yes, happy birthday. I forgot to say it earlier this morning. I walked in the rain this morning. Good morning. So these sentences will be the result set when you're searching for morning as the end word of a sentence. So using morning dollar, you will get this kind of data. These are just examples I'm giving. So it all depends on the type of analysis and what is your objective in doing that analysis. So next I'll give you the square brackets. What are they useful? So for example, uh, let's say we are looking for the exact word bush denotes George W. Bush. These are examples I taken from online free resources. So these are just very good examples that help explain. So that's the reason I put in my slides. So we can list a set of characters you will accept at a given point in the match. For example, I want to take both case sensitive letters. So case sensitive as well as like case insensitive letters actually. So both capital and normal letters. So I can take BBUUSSHH, which the second part is actually the smaller. So which means any possible combination is will match the line. For example, small b, capital U, capital S, small h, any kind of combination, any possible combination with those eight. The first combination will be either capital B or small b, second will be capital U or small u. So any possible combination, we will get the match of the line. For example, the Democrats are playing name the worst thing about Bush. So the Bush here, the capital B is followed by small USH. So next you have I smell the desert creosote Bush brownies barbecue chicken. So you have Bush here, which everything has small case letters, and BBQ and bushwalking and knowledge. Again, Bush here is small letters, and Bush told you that North Korea is part of the axis of evil, and Bush here, which has capital B, small USH. I'm listening to Bush Hurricane album version. So again, so you're getting multiple. So you get the point. So capital B, any kind of combinations will be extracted by using the square brackets. So if you want to have like multiple sets of words, so you can use the square brackets. The entire list of characters that you can accept can be put in this. So again, I'm trying to include uh, two or more meta characters now. So I'm trying to extract here the example just starts with exponential. Inside the square brackets, you have li followed by am. So which means sorry, it's not li actually, it's capital I, small I followed by am. So I'm trying to look for a sentence which is starts with I am and the I doesn't necessarily be case sensitive. So for example, you can look at the following sentence. Okay, the first sentence: I'm so angry at my boyfriend, I can't even bear to look at him. So, sorry to put that look at him here. This actually belongs to the first sentence. So, I'm saying this sentence is a result of this math. So, I am boycotting the Apple Store. You're getting that's the result. Here, I is capital. I'm twittering from iPhone. I'm a very vengeful person when you lose my sweetheart. I'm so over this. I need food and bacon. So, these are just random people text. This is one of the advanced analytics being done in any company for using the text or Twitter feed or Facebook feed or LinkedIn feed or any kind of feed. So now here I have combined two meta characters. uh, Starts with capital I, small I, and space am. So moving on to the next one. So again, still using the same square brackets. So what else can you can specify in the square brackets? You can specify anything that comes to your mind. For example, you can specify a range of letters A to Z or A to Z, capital A to Z. Notice that the order doesn't matter. The order actually doesn't matter. It may be capital I, small I. You can give small I, capital I. The order is not going to matter. So if I put A to Z, any character that belongs to the 26 alphabetical letters of alphabets of English, so you will get it. So here, let's say I'm looking for a string which will have which is followed by a number, which starts with a number followed by a character, followed by any character actually. Uh, so here it's actually it starts with a number followed by a character. So, for example, seventh inning stretch, second off soon to begin, 3 a.m. can't sleep, 5 feet 7, first sign of starvation. So, these are all sentences where you have the first character as a number followed by a second character which is an alphabet. So based on this you can so let's say if you're extracting some IDs from a person. For example, if in any college in India you will find the ID to be a combination of numbers plus uh, numbers plus characters. So in this case, you can use to these kind of regular expressions to extract the IDs. So next, moving on, when used at the beginning of a character class, the hyphen, the exponential symbol, is also a meta character, and it indicates matching characters not in the indicated class. For example, so what does it actually mean? Is that so? The first one, it starts with a question mark symbol dot inside the set bracket followed by dollar. So it will it indicates a matching characters not in the indicated class. For example, you are searching for something called a dot. So for the examples that match with these lines are I like basketballs. 6 and 9, don't worry, we all die anyway. Not in Baghdad. Helicopter underwater. So what really happens is you are searching for question mark and dot, and which ends with dollar. So if you are looking for a character that ends with the dot, it will not fetch this. So it indicates matching characters not in the indicated class. So any sentence that ends with question mark or dot will be avoided from the sentence. That's the simplest way to put it. Any sentence that ends with dollar or dot will be excluded. So yeah, as you can see here, no sentence will end with dollar. All the sentences that does not end with question mark or dot are being pulled out for the result set. More meta characters like dot is used to refer any character. So 9.11 will match anything, literally anything. So you have 9. It's stupid to post 911 rules. If any one of us did 9/11, 9 class 11, 9.11, 9:11, and here you can see 9911. So this 9 is also a match. So as you can see, the dot, which means it can be replaced by any character, which means you're looking for a string which has 9 followed by any character and followed by two ones. So you're trying to extract this. Okay. So what are we trying to do next is like you are trying to get characters which specifically use OR condition to extract certain specific variables. For example, in the this does not mean pipe in the context of regular expressions. Instead, it translates to OR. So we can use it to combine two expressions, the sub expressions being called alternatives. So alternatives are nothing but using OR condition to extract certain specific strings that is needed. For example, flood, a single straight line followed by fire. The single straight line, it is a keyboard character, so which is near the plus symbol in the keyboard. So you can use that. This is nothing but a symbol for or. So normally people used to say it is or only. So flood or fire will match the lines. Is fire wire like USB or non-max? So this gets a match because we have fire in the sentence. And the next thing, the global flood makes sense within the context of the Bible. The flood. Yeah, I have added the fire onto it. And the floods, hurricanes, killer heat, rednecks, gun, etc. So yeah, flood or fire getting a match. So that's the reason you are getting all these strings into the data set. So, there is no limit to the number of alternatives you can list. So we can include any number of alternatives: flood, earthquake, hurricane, cold fire. So which we were trying to match any kind of disaster that happened. So you can see all the strings that matches with have not a whole lot of hurricanes in the Arctic. We do have earthquakes nearly every day somewhere in our state. Hurricanes whirl in the other direction. Cold fire is straight because we keep getting earthquakes. So all these sentences have any of the four strings: flood, earthquake, hurricane, cold fire. So that's the reason we are trying to get all these four characters, all these four strings out of the feed that is coming from. Even more alternatives I want to bring into this. So, and not just literals, I want to bring real expressions that so you are trying to extract any sentence that starts with good or bad, and the sentence may start with a capital letter or a small letter. So I've given G followed by G, the GG, which means any of the character G or G is allowed, and any of the character B or B is allowed. So this will match the lines. So for examples, so good to hear some good news coming from someone here. Uh, Good afternoon, fellow American infidels. Good on you. What do you drive? KD guess they had bad experience. My middle name is Trouble and it's bad news. So here you got a sentence. Good to hear. Good afternoon followed by good, good, and here got bad here and bad here. So what is the reason for us? The start simple. It's actually looking for the first set of expressions. The start, the exponential symbol will tell you the sentences that start with good alone and not bad. This R has limited this exponential to be used only for good, and this bad is not limited by it. So that's the reason we are getting the bad experiences when bad news in the next set of characters. And so now till now we have used or. So next we can start using and. So, sub expressions are often contained in parentheses to constrain the alternatives. For example, this sub expression, this exponential symbol, the previous example, we saw exponential symbol followed by good and followed by r. For example, this. So here, this exponential symbol was, forget the exponential, this is a start. Remember it as start. So it is related only to this, and any sentence which has bad will come in. So that's the reason this sentence, even though it didn't start with bad, but it had bad, the word bad in the sentence, and that's the reason you're getting this. Same way this sentence also. Now, if I want to find a sentence which starts with good or bad both, either way, so I'll get sentences only that starts with either good or bad. For example, bad habit, bad coordination today. Good because there is nothing worse than a man. And bad cop, it's because people want to use drugs. Good Monday holiday, good riddance to Limey. So these are sentences that will help you understand the usage of the start symbol followed by parenthesis. This parenthesis, which means the entire start symbol is applied to both. So more meta characters. So what is this question mark? So the question mark is actually something that indicates, it's a meta character that indicates that the indicated expression is optional. For example, uh, George W in bracket, square bracket, and followed by dot. Bush will match the lines. So this meta character question mark will ignore this W Bush, George W Bush. So in this you'll have uh, the sentences, I bet I can spell better than you and George Bush combined, which means George Bush here doesn't have W, which means this the entire case is optional. So BBC reported that President George W. Bush claimed God told him to invade Iraq. So this W Bush is also coming here. A bird in the hand is worth two George Bushes. So again, you are getting sentences which doesn't have W. So which means that the question mark here is used uh, to remove, to give optional sentences that needs to be extracted. So there is one thing to note here in the following. So we wanted to match a dot as a literal period. To do that, we had to use that slash escape. The reason I use the slash, which means it tells you that we saw earlier the dot used for any character that can be filled in. So dot is also a meta character which significantly in which indicates that any kind of character can be filled in. So to denote that here in this sentence the dot is actually a dot, we need to use the escape sequence slash. So this meta character dot is actually becoming a character itself. So to do that we had to use the slash escape, the meta character preceding it to the backslash in general. We have to do this for any meta character. Forget dot, you should use the slash escape sequence for any meta character, so that we want to include the match. I wanted to find a match for dot, that's the reason I used a slash. So there are much more meta characters in the uh, R programming language. What are those? Like star and plus. The star and plus signs are, the meta characters used to indicate repetition, and star means slash any number including none of the item, and plus means at least one of the item. This is the same as any regular expression as well, which means star is like it starts from 0 to infinity. I mean, it's 0 to n, and plus indicates it's 1 to n. So you want to have uh, any sentence, you want to have any sentence. Let's say you want to have a sentence which dot star, which means any sentence that has a single character should be printed. So anyone want to chant hello 20 here, he means older man, question mark, square brackets, brackets 20. So these have any characters. This it starts with any character. It has some character. Anything that has null characters also, this is also null character, so this is also printed. So that's the reason we are using dot star. For example, so now we want to use plus signal. So in this you are using 0 to 9, any character from 0 to 9 is accepted, plus dot star 0 to 9 plus. So any sentence which has a number followed by anything and followed by nothing also followed by number will match the lines. So here you have 720 MP battalion 42nd brigade. So here you have a number followed by a number. So this is giving a match because dot star, which will contain no values also, and here also we have 2 or 3. For example, we have 23 here, maybe this is the reason this data got in, or same way for any number. So you have 2 or 3 years, which will also give a match, and 3 or 4 days, which will also give a match. For me to go to bed again, to go to, for me to, everything will be a match for this sentence as a number followed by any set of characters followed by a number. This can be any set of numbers actually, like 40, 23, or any numbers. So that's the reason this is for repetition actually. So a number followed by a number here is also a match, a number followed by a number is again a match, a number followed by characters, a number again a match. Same way it goes on for any set of examples that needs to be extracted like this. Now moving on, uh, what are the next set of meta characters? So we have interval quantifiers, which is like using set the brackets here. The let us specify the minimum and maximum number of matches of an expression. For example, here Bush starting with a B and small b plus starts with plus plus 1 comma 5. So we are setting the minimum and maximum number of matches 1 and 5. So Bush has historically won all major debates he has done, so this is one match. Bush doesn't need those debates. Bush doesn't need the debates. Maybe you're right. That's what Bush supporters are doing about the debate. Bush was poorly prepared to the debate, indeed, but still Bush should have taken the debate more seriously. Keep it in the Bush smoked. So here you have sentences that starts with Bush, that has Bush in it, everything. So that's the reason you are using plus. So any kind of repetitions is allowed. Maximum number of repetitions is 5. Minimum and maximum number of matches is 5. So this will give you all the list of examples which has the word Bush in. So um, in that set of regular expression, you're setting the minimum. And so for example, if I use that brackets to specify m comma n, at least m but not more than n matches, which has at least one matches. So here it was set as 1. So if it is set as 2, it will look for at least 2 matches in the sentence. So m means exactly m matches, m means m, comma means at least m matches. So again, revisiting the already did once, in most implementations of regular expressions, the parentheses not only limit the scope of alternatives divided by a j, but also can be used to remember text matched by the sub-expression enclosed. So we refer to the match text with /1, /2, etc. So the expression plus followed by a to z plus and plus /1 plus will match the lines. So it is like any number of repetitions allowed for small characters to capital characters. Repetition is allowed. So plus followed by slash one. So this one actually is meant for will match the lines. Time for bed, night, night, Peter, blah 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 blah. My tattoo so itchy today. So these kind of sentences, any kind of sentences will be matched by this regular expression, which will give you the repetitions of plus. So like the star is greedy, which means like it always matches the longest possible string that satisfies the regular expression. So a sentence that starts with S followed by dot star S matches. This dot star is a repetition for any character. Any character star means it starts with S and finishes with S, and here the entire set is matching. For example, sitting at Starbucks, setting up MySQL and Rails, studying stuff for the exam, spaghetti with marshmallows, stop fighting with crackers, sore shoulders, stupid economics. So all these start with this and ends with this. Even any kind of long sentences is matched by this. So if you want, like it can be turned on with the question mark symbol, as in question mark starts with s dot star question mark s dollar. So coming to the summary of regular expressions that we saw today. Regular expressions are used in many different languages. It's not unique to R, but still it's a very useful thing in R to do for text analytics. And regular expressions are composed of literals and meta characters that represent sets or classes of characters or words. And text processing via regular expressions is a very powerful way to extract data from unfriendly sources. Not all data comes as a CSV file. This will end the regular expressions. Now we'll see about classes and methods in our programming. So like same as the object oriented programming concept is not new to anyone, but this is a system for doing object oriented programming. So R is basically is originally quite interesting because it is with both interactive and as a system for object orientation as well. So you should be knowing this. But other languages which support object oriented programming are C++, Java, Lisp, Python, and Perl. And generally speaking, like they are not interactive languages. In R, much of the code for supporting classes or methods is written by John Chambers himself, the creator of the original X language, and documented in the book Programming with Data, a guide to this language. So if you want to see the classes or methods for R programming, if you can refer Programming Data, a guide to this language by John Chambers. A natural extension of Chambers' idea of allowing someone to cross the user programmer spectrum. So object oriented programming is a bit different in R than it is in most languages. Even if you're familiar with the idea, you may want to pay attention to the details because the, the usage of classes and methods and the concept of object oriented programming in our program R is very different than the rest of the other languages which employs object oriented programming. So there are two styles of classes and methods. What are those? There are S3 classes or methods and S4 classes of methods. And like the first S3 classes or methods will have like, so they are included with the version 3 of the S language. So they are little informal. Sometimes they are called as old style classes or methods, and S4 classes or methods more formal and rigorous, and it includes with the S plus 6 and R 1.4, and they are called as like the new style or classes or methods. Now we'll see in detail about S3 classes or methods, S4 and S4 classes or methods, and we won't be seeing in the programming language because S3 classes are not supported in the current R programming. So I'll give you examples which will be in the slides themselves. So they are like the S3 classes and S4 classes are, two worlds living side by side. So for now, S3 classes or methods and S4 classes or methods are separate systems, but they can be mixed to some degree. So each system can be used to fairly independently of each other. Now, developers of new projects are encouraged to use the S4 style classes or methods. So they are used extensively in the bioconductor project. These are like open source projects which are run using the R programming languages. And but many developers also use S3 classes or methods because they are quick and dirty and easier. So in this lecture, we'll focus primarily on S4 classes or methods. The code for implementing S4 classes or methods in R is in the methods package. So there's a package called methods I would have shown you earlier, and this is loaded by default, but you can also load using the library command, the library of methods, if for some reason it is not. Object oriented programming in R. A class, what is a class? A class is a description of a thing. For example, like the classic example that were used for describing object oriented programming is, you can take a car. A car is an object, and what are the functions of the car, and what are the parameters of the car, like the engine, the accelerator, the wheel, everything forms, and the forms the entire object, the car. So a class can't be defined using set class in the methods package. An object is an instance of a class. Objects can be created using new. So a method is a function that operates on a certain class of objects. A generic function is an R function which dispatches methods. Generic function typically encapsulates a generic concept. Example: plot, mean, predict, etc., etc. So the generic function does not actually do any computation. Method is the implementation of a generic function for an object of a particular class. So moving on, uh, we need to see about methods further. The generic function, like so a generic function I told you which dispatches methods, it typically encapsulates a generic concept. So the method is the implementation of a generic function for an object of a particular class. So what are the things to look up when you are going for object-oriented programming in R? The help list for the methods package or extensive. So do they read as they are the primary documentation? They will be available in the CRAN website. So you can get the documentation, primary documentation for R programming. So you may want to start with classes and methods. You can check out set class, set method, and set generic, so which are very much useful in object oriented programming. And there's some of it gets technical, but try your best for now, like it will make sense in the future as you keep using it. So most of the things like class, set method, and set generic will be useful to you when you are trying to implement the object oriented concepts in R programming. So most of the documentation in the methods package is oriented towards developers or programmers, as these are the primary people using class or methods. So if you want to become a very good developer or programmer in object oriented programming using R, then it's always suggested to read those documents, the development documents in the methods package. So here I've given a specific examples. So all objects in R have a class, so which can be determined by the class function. So let's say there is an object called 1 and you want to see what does it belong to. So we know it is numeric. So if you want to see whether the class of 1 is numeric, just type class of 1 and it will return you numeric here. So if I want to see class of 1, so it says numeric. Same way I can see class of true, says object true is not found because I didn't enter in caps. So logical. So again, class of random numbers of 100. So again, it's a numeric. So the same way, class of NA is logical, class of FFO is character. So anything. So anything related to the classes. If you want to find a class of an object, just use the function class, which will tell you the class of the object that is created. So data classes go beyond the atomic classes. So let's say we have a random number set of 100, for example, control L, clear the screen, and again I'm creating y x plus r norm 100. Now I have x comma y. So if I'm trying to create a linear regression model, nothing else, fit. So this fit, the class is LM, which is the linear model. The linear model is the class of fit, which is given by the class function. So next we'll come to generics or methods in R. So there are S4 and S3 style generic functions. They look different, but conceptually they are the same. They play the same role. So when you program, you can write new methods for an existing generic or create your own generics and associated methods. Of course, if a data type does not exist in R, so let's say that matches your needs, you can always define a new class along with generics or methods that go with it. So if you want a data type to come into the R programming system, but it doesn't exist in the set of data types in R, then you can define your own generic or methods and then create the data type you want. An S3 generic function in the base package. So I'm giving you a small example. This is the one of the S3 generic function in the base package, the main function. So the main function is actually generic. So if I put mean, so how to use this method, bytecode, environment, namespace based in the base package. It's a function of x comma etc etc. So uh, again, there are a lot of um, functions, generics. So again, print, same way, like main print. So a lot of functions are there in the base package, generic functions. So you can see those in the base package. And, so S3 methods, it's like, let's see, methods of main. So you have main.date, main.default, main.difftime, main.posixity, main.posixity. So you have this many sets of S3 methods associated with main. So next we'll see about an S4 generic function. Again, this is from the methods package, and S3 was from the base package. So what is there is the print function in the S3 generic class. So like we have a S4 equivalent for that, which is called show. Now if I use show, you'll get it's a standard generic for show, defined from the package methods. It's a function of object, standard generic show, bytecode, environment. Methods may be defined for arguments, object use methods, show for currently available ones. Now like we saw this standard generic for show, defined per package methods. These all we saw in that R module. So yeah, as you can see here, this generic function excludes non-simple inheritance C setters. So it's not not called directly. So because objects are auto printed. So if you just print, if there is an object called X, you just print X, it will automatically print it. So that's the reason we don't use show as much. Now we will see some more S4 methods. So there are many different methods for the show generic function. If you want to see the different methods for the show controller, I'm clearing the screen. Show methods of show. If I use this, you'll see the function show. You're seeing the package methods. So class generator function, class representation, environment of class function, generic function with trace, method definition. So you see all these objects associated with the show. So uh, there are many different methods to the show generic function. So what is the mechanism behind generic method or generic normal methods? So the first argument of a generic function is an object of a particular class. There may be other arguments as well, but the first argument should be of a particular class. So the generic function checks for the class of the object. A search is done for example, if you call for show, the show is searched in the object fab, the methods package for finding the generic function. That is, a search is done to see if there is an appropriate method for that class. If there exists a method for that class, then that method is called on the object, and we are done. So if a method is for that class does not exist, a search is done to see if there is a default method for the generic. So if the method is not there, then a generic is searched. So if a default exists, then the default method is called. So like if you're searching for a method, it will search for the method, and when the method is there, it will display it. So if the method is not there, then it will look for the generic function that's associated with it, and if the generic function is available in the packages, then the generic function, the default method is called. So what if the default method is not there? Then an error will be shown. So if a default method doesn't exist, then an error is thrown. So let's move on to we need to examine the code for methods. So how do we do that? So examining the code for an S3 or S4 method, it requires a call to a special function. So you cannot just print the code for a method like other functions, because the code for the method is usually hidden. A method for the print or show that we saw earlier, so the code for these methods is hidden. So you cannot just print the code for these methods because it is hidden. If you want to see the code for an S3 method, you can use the function get S3 method. So the call is get S3 method generic comma class. For S4 methods, you should use get method. The call is get method generic signature. More details we'll see it later. So I already told you to use this seed when you are working with random numbers, to remember what was the random number, because random numbers always change when you use the function again and again. So we use seed to set the defined random numbers at the time. So what is happening here? I'm using set.seed of 2, which means I'm creating the seed, and x I'm assigning 100 random numbers with normal distribution, and I'm finding mean of x. The class of x is numeric, but there is no mean method for numeric objects, so we follow the default function for mean. So you as you can see here, the mean method does not exist for numeric objects, but the default function for mean is being called so that you get the result at the end. So next, what happens is head of get s3 method mean command default. It's a function x trim equal to 0, na dot remove equal to false, which means I'm not removing the dot na values. So if not dot is numeric of x and is dot complex x and not of is dot logical x. What am I checking here? I'm checking whether it is not numeric or not complex or not logical. So then I can display a warning: argument is not numeric or logical, and it returns NA. So Now in the tail function, so let's say there is a tail function I'm creating, where the next function here I'm creating is a get s3 method mean comma default lo equal to 4 floor of n comma n star trim plus 1, and I'm just creating a high low function here, simple, and high equal to n plus 1 minus low. So if I sort like x equal to sort dot int of x comma partial equal to unique, the unique will contain the c low comma high and dot internal mean of x. So this mean we are calling the default function for this function that we are creating now. That is the reason we go for this s3 method here to call the default methods for uh, mean. So now we are going to the example 2, like what happens here. Set.seed of 3 df data.frame. I'm creating again a data frame which has random numbers 1 to 100 in the x column, and in the y column we just have 1 to 100 listed. So I'm using sapply df comma mean. So what happens here is x value created, and for mean y. So the class of df is data frame. So in a data frame, each column can be an object of a different class. So here we have a numeric objects. Again, we have numeric objects. So we apply over the columns and call the mean function. In each column, the mean actually checks for the class of the object, and it dispatches the appropriate method. So we have a numeric column and an integer column. So the first column is a numeric one and the next column is an integer one. So in both the cases, mean calls the default method. So that's why like we are able to get the mean values here. Now we'll see about the calling methods. Some methods are visible to the example. For example, the mean that we are using it earlier, mean dot default. But you should never call default methods directly. Rather, you can use the generic function and let the method be dispatched automatically. If you write new methods for new classes, you'll probably end up writing methods for the following generics as well. Print or show, summary, plot, and a lot of other things. There are two ways that you can extend the R system via classes or methods. Write a method for a new class, but for an existing generic function, that is like print. Write new generic functions and new methods for those generics. Now, why would you want to create a new class? Now we are going to S4 classes. So why would you want to create a new class? So to represent new types of data, example like gene expression, space, time, hierarchical, sparse matrices, anything like any kind of data. So new concepts or ideas, maybe those have been not yet thought of that yet. A dotted point, process model, mixed EECTs model, sparse matrix. These are examples of like advanced topics in science and technology, which haven't been thought of yet. To abstract or hide implementation details from the user. I say things are new, meaning that art does not know about them. Not that they are new to the statistical community, but they do not know about them. So if you are working in a very different field, very niche field, which is not related to any way close to R programming, so you can create new classes with for your own purpose. So creating a new class in S4 or a method. So a new class can be defined using the set class function. At a minimum, you need to specify the name of the class. The name of the class first, it's a mandatory one. You can also specify data elements that are called slots. You can then define methods for the class with the set method function. Information about a class definition can be obtained with the show class function. Now, now we are seeing the S4 class or method, the polygon class. So creating new classes or methods is usually not something done at the console. You likely want to save the code in a separate file. Now, I want to create a uh, I want to create a class polygon with a representation of x as numeric and y as numeric. So let's create the polygon in R. The name of the class is polygon representation of x numeric comma y equal to numeric. Now the class is created. So again, in this, the slots for this class are x and y. The slots for an S4 object can be accessed with the at operator, at the rate of operator. So plot method can be created with the set method function. So a signature is a character vector. So we saw that S4 class method needs a set method and a signature. A signature is a character vector indicating the classes of objects that are accepted by the method. In this case, the plot method will take one type of object, a polygon object. So set method plot polygon function x comma y followed by the elliptical symbol, and plot of x at x, x at y, which means I'm plotting x at x and x at y. At function is an operator. At is an operator used to extract the slots for a polygon. So type equal to n followed by ellipsis. So xp equal to c of x at x of 1, and a yp equal to c of x at y and x at y of 1. Lines xp comma yp. So this will create a plot method which will plot the polygon in the. Notice that the slots of the polygon, the x and y coordinates are accessed by the out operator. As I mentioned earlier, at is the operator which will help you access the slots for polygon. So the polygon class, what are the steps for? So you are creating a new class, set class of polygon representation x numeric, y numeric, and you are creating a plot method for this class. Set method of plot, you are using polygon, the function of x comma y, and you are just using plot. Type in lines of xp and yp, and you are just calling the function plot. So after calling this set method, the new plot method will be added to the list of methods for plot. So show methods of plot will give you the function plot and the package graphics, and x equal to any x equal to polygon. Notice that the signature for the class polygon is listed. The signature is the x equal to any, y x equal to polygon. The method for any is the default method. So it is for whenever, even I have defined for polygon. So but even then any appears because it is a default method when it is called, and when now other signature matches. So with this, we complete classes and methods. So for further readings, there are like quite a few examples on CRAN which use the S4 classes or methods. Bioconductor.org. This is a rich resource even if you know nothing about bioinformatics. So some packages on CRAN as far as you know: SPASM, GPC library, XMEX, ITS, LME4, Orient, LIB, PixMap. So the stats4 package comes with R as a bunch of classes or methods for doing maximum likelihood analysis. So with this, we complete the classes or methods. We will see about part 2 of the debugging process. So what are the something good things about debugging is that, like, how do you know that something is wrong with your function? So there are like multiple test cases you need to write when you are debugging for bugs, debugging for bugs in your code. So what was your input? and how did you call the function, what was the result that you were expecting, output messages or any other results, like, and what was the actual result that you got, and how does what you get differ from what you were expecting, were your expectations correct in the first place, can you reproduce the problem exactly in the same way. These are all some things you need to think about before going to the debugging process. So what are there are some primary functions tools for debugging functions in R programming. There is this traceback. So traceback, what it normally does is that it prints out the function call stack after an error occurs. So it doesn't do anything, but it just tells you like what are the steps that happened when the code was run. So you will be able to trace back exactly step by step what really happened when the execution of the code. Debug, it flags a function for debug mode, which allows you to step through execution of a function one line at a time. And browser, it suspends the execution of a function wherever it is called, and it puts the function in debug mode. So debug mode is flags a function, but browser it actually suspends the execution of a function when it is called and puts the function in debug mode. So trace, it allows you to insert debugging code into a function at specific places. And recover allows you to modify the error behavior so that you can browse the function call stack. So these are interactive tools specifically designed to allow you to pick through a function. There's also the more blunt technique of inserting print cat statements in the function. So you can optimize or customize according to your wish. So traceback. So when you use mean of x and error in mean of x object x not found, so traceback will list. Now here we have only used one line mean of x, so it traceback gives you the step one as mean of x. If there are like multiple steps executed, to list all the steps that are in the code. For example, a linear model of y as y to x. So error in evaluation expression environment enclosed object y not found. So you will see that the object y does not exist, but there is an error. That's the reason for the error. But when you trace back, so it will give you, it starts with the line first in eval of expression. This eval of prediction various data environmental risk. These are the functions that were called when you type linear model of y to x. So model.frame.default formula y to x, drop.unused levels true, model.frame formula y to x. So this is actually in the reverse level. That's the reason it's called traceback. So actually the execution started from here, lm of y to x till this. So this was the last line, and in this, if environment variables y is not found, and hence the error in evaluation expression environment enclosed object y not found. So now the debug code. The debug of lm will give you debugging in lm of y to x, debug return x to x, return y to y, cl match.call, z $qr equal to null, and rows of 2. It goes to the next line. So debug is a function which used to, it gives you line by line of the call. So again, the continuing the previous code from browse to. So if we have browse to n, debug return x to x, and each and every single call has been y is given to y, n match.call expand on dots, and in this region until this the match it's matching for the arguments that exist for y and x. So recover. So options of error equal to recover. So read.csv of no such file, which means I'm just indicating that there is no such file in the directory. So I'm just using the recover. So error in file of RT cannot open the connection. In addition, a warning message in the file RT, it cannot open the file no such file because there is no such file or directory that exists. I'm just given the name as no such file. So enter a frame number or 0 to exist. So read.csv of no such file, read.table of file equal to file, header equal to header, scp equal to scp, quote equal to quote, equal to file, file.rt selection. So with this, we come to the end of debugging. Using debug, recover, and trace back, you'll be able to optimize the debugging process much more further. So in the summary, you're getting three main indications of a problem or condition: message, warning, error. Only an error is fatal, but the message and warning will allow the execution of the program, even though there is some mistake or some kind of warnings. Warnings might, you may, if you are aware of it, you can ignore, but it always instructed to take care of the warnings as well. When analyzing a function with a problem, make sure you can reproduce the problem, clearly state your expectations and how the output differs from your expectation. So interactive debugging tools, traceback, debug, browser trace, and recover can be used to find problematic code and functions. Debugging tools are not a substitute for thinking. So that's it. We are done with debugging, and with this we'll close the debugging process.